Should reflect. Still waiting for my YouTube notification. Yeah, okay. You're live. Cool. All right, so today's schedule is going to. Hey guys, welcome back. So we had a couple of sessions yesterday. I hope you guys were able to watch it. If not, you can just hit the channel button here on YouTube, and you should be able to see yesterday's stream. Today's stream, we have a lot more. I think we have 4 or 5 different sessions. With the first session being a quick one. So Anul is here. He's going to be talking to all of us about Hackaday, and actually, there's a bunch of sites which Hackaday manages. Essentially, I don't know exactly how it works, but I love 2 or 3 of them a lot. Tindy is one of them. Hackaday is another. But anyways, without further ado, I'm going to hand it over to Anul, and me and Siddesh are going to step off so Anul can talk us through that.
Awesome. Thanks, Anuj. I'll straight away run to share screen. I want to take up a lot of time today, and let's start with present. This is a question I get asked often. So I thought it might be a good way to just kind of introduce you to the whole Hackaday ecosystem because there's quite a bit besides just Hackaday. Obviously, there is the blog, which is where it all started many years ago. Some of you might be knowing Filteron, who is now at Adafruit with Lady Ada. So he wrote the first blog post for Hackaday. Right now, it's a bunch of, let's say, a team of writers from around the world who do the blogging part. So it's a fairly big team, fairly multi-dimensional, spread over continents and so on. So someone or the other is writing throughout the day. A lot of people end up asking me, how do you, what makes a good Hackaday blog post, for example? So, as writers, what we are looking for is obviously an interesting hack, something that you've done. Maybe you've made something new, maybe you repaired something, maybe you fixed something. But what makes it good for us is a good description of what you've done with some pictures, maybe a video, and all of that put in a blog. And if you don't have blogging it on your own, then I can. There are a lot of other online places where you can do it that I'll talk about in a bit. But essentially, if there is a tip that you want to give, then the best way is to go to the hackaday.com webpage and click on the submit button over here. So that brings up a little form that asks you for your mail address, subject, and something about a link. And what happens once you do this is it goes to a backend where we have a Google group, and all the tips land up over there. And writers like me and my colleagues, they keep scanning. They keep scanning this list for interesting tips that they can write about because uh, not everyone can write about every topic or every subject. There are some subjects or topics that I kind of am comfortable with compared to others and so on. So each writer picks up what they would like, uh, seems interesting to them, and then the writer, the editors then kind of sometimes polish it up and so on, and then it goes to a scheduler. So sometimes from the time it gets written to the time it gets published could be a week or two. Sometimes it gets published immediately and so on. So that's how the submit a tip works. And if there are, let's say, if you're looking for certain specific authors, and since this is a WordPress website, there are many ways of looking for stuff. So if you do /author/name, uh, you can look for all of the the blog posts that I have made, for example, or all of the blog posts that someone else has written, for example. So that's the whole. This is like the main website. That's hackaday.com. We also run a lot of series of blog posts which are pretty interesting. Like one of them is Ask Hackaday. And usually this starts with a question of what an engineer might be looking and answer to. For example, ask Hackaday, what's in your fastener bin? So what kind of screws or fasteners are there, and so on. And then it goes on to describe more about stuff, or what kind of tools do you really need for life on the road, and so on. So these are interesting pieces that, as engineers, are useful or kind of interesting for us. There's also a nice series on Linux called Linux Soup, which is pretty interesting for all of us, of course. So you can look for that. And then there's other stuff like Embed with Elliot. So Elliot writes about embedded electronics. We have Retro Tectacular. We write about old, let's say, technology that's interesting. So basically, maybe someone takes up a really old video on YouTube, for example, describing some ancient computer, for example, and stuff like that. So we kind of write about old stuff in this. And this is also very interesting. Uh, Similarly, there's a fail of the week. It doesn't happen every week, but when we get a submission for a fail, it usually gets branded as fail of the week because you don't get one every week, but they're quite few. And sometimes we get tips or submissions which don't justify a whole blog post. So we kind of just accumulate them as a kind of weekly Hackaday links blog, which might contain about 8 or 10 different links with one or two, paragraph of description showing, talking what that link is about. Then there's a new part day where we kind of write about new stuff like the new RP 2040, for example, and so on. So new or interesting components. A new LiDAR has come in the market. We kind of write about it. And then there's this week in security, which is also kind of pretty interesting because it does a roundup of security related, let's say, news events around the world. So these are the kind of regular, let's say, articles or series that we write at Hackaday. There's also original long form posts that we as writers do that is not a part of someone else's blog post. So, for example, I've written a couple of them, so something like, let's say, new features on KiCad or how to do project management with KiCad. I also wrote another one on how bicycles are hacked and abused and used in India and so on. So those are original long post articles which are not actually someone else's work, but they are kind of written directly by the writers. And finally, there's a podcast. So this is an interesting roundup. If you're driving or if you're doing some soldering and want to listen to some nice stuff in the background, a podcast can be a nice companion. So there's a weekly podcast which is hosted by Mike Stish and Elliot, and they talk about different, let's say, topics or stuff that we've written about on Hackaday during the last week, and they're interesting, or their favorite blogs or their favorite hacks and stuff like that. So there's a lot of stuff on Hackaday for each one. It's kind of impossible to read each and every hack that we write about every day because there are quite a lot of them now. I think almost 8 or 10 blog posts every day. So as writers, or as a writer, even I am kind of finding it impossible to kind of keep up with all of these blog posts every day. But some of these series and some of these, let's say, links can be pretty handy or interesting. So that's the main, let's say, mothership. That's Hackaday.com, and was pretty close to closure several years ago. There was even a crowd-funded campaign to try and raise funds to keep it afloat. But then, luckily, Supply Frame stepped in. They bought Hackaday, and they have invested a lot in not only sustaining it but making it grow quite well by a lot of new additions and new properties that have been added. So that's been a great. The next one is the project repository, which we call the Hackaday.io. And to start with, if you have any, let's say, queries, questions, or if you have complaints, then you ought to refer to Lutetium. That's the channel that is, let's say, read by the backend guys who do the programming and stuff like that. So if you find any issues with the website, if you add Lutetium, you should be able to get their attention to, let's say, fix something with the website that's wrong in terms of formatting or for wrong information and so on. But what Hackaday.io offers essentially is a place to host your, uh, let's say, projects. So if you don't have your own blog post or your own website and you'd still like to, share what you're doing with other folks, then this is a place where you can, set up your own projects. There's a ton of, let's say, different projects being hosted over here every day with all kinds of stuff, 3D printing, electronics, computers, you name it, and everything's being done over here. Also, all of the hackers are hanging out here, so we have what's known as the chat channel, which is pretty much like if you have been in the olden days used to relay chats like IRC, and this is like the modern equivalent of that. Uh, Main chat room is called Hack Chat, obviously. There's also specific chat rooms, for example, for Tindi, or if there is a conference happening, then we'll set up one for a conference and so on. Like for the Remoticon, we had one. The other thing the project website does is a contest. The biggest and chief among them is the Hackaday Prize that has been happening since I think 2015. I don't remember the exact years, but yeah, it's been running for several years. It's a pretty big competition, and essentially every project that is submitted on the .io website qualifies for that annual event. And the prices are kind of pretty interesting and amazing. But more than that, the submissions, the kind of projects that people come up with, it's really eye-opening to see the different hacks that people do. So again, it's kind of very difficult to keep up with all of the action, but I'm sure you can find something that suits everyone's interests over here. Uh, the Hackaday Prize isn't the only competition that happens annually. It's like just last month, I helped judge this contest, which was called the Goodbye 2020 contest, and this was pretty simple. How do you want to get rid of 2020, or how do you want to say goodbye to this awful year? And there were prizes sponsored by DGP, and there were some amazing entries and stuff like that. So lots of contests. If you look at the contest tab, you can either check out the old ones or figure out how you can, let's say, participate in the upcoming ones. Then we have what's known as it's, I think supposed to be a weekly event, which is known as Hack Check, where we invite someone and do a kind of a text chat with them. And the last one was on the ESP32S2 and the RP2040. So we had Lady Ada on board, and there were a couple of other hosts. I think there was Phil Caron as well. So 3 or 4 of them came up on Hack Chat, and all of us can either chat with them, ask questions, and so on. And it's really interactive and live. But These also get recorded as transcripts. So here is the transcript for the last one, for example. It kind of goes all the way through. And if you look at this list, this is what we've done up till now. In 2021, we've had these three hack chats: plant communication, movie magic, and ESP32. And there's many more that are coming up, which get announced regularly. So if you sign up for the newsletter, it should be the easiest way for you to figure out what's coming up. The other thing is a stack option, which is kind of interesting if you are looking for some specific help. If you're looking for, let's say, hiring someone, or if you got stuck with something and you need someone to help you out with. If you want someone to collaborate with you on a project, this is a place where you can kind of, it's like a jobs board, but a lot more actually. So Stack can be a pretty interesting place to hang out. And then we have courses. This was done recently, and this goes by the name of Hackaday U, U as in university. And there's lots of interesting courses over here. There's stuff on AVRs and there's stuff on Rhino. And I did one on KiCad and FreeCAD. There was one more by Ion. Uh, yeah, Introduction to FPV Drones by Ian, who's going to be talking to us later today on this topic. So these are pretty interesting courses. They're usually video series, but there is also obviously a project page for each one. Like here's mine with a description of what the whole course is about. There's links to all the different sessions we had, and then there is a link to the actual video for that session that covers up all of these timelines. So as part of the Hackaday University, where we are kind of regularly doing fresh courses on topics of interest for hackers. And of course, all of these are free to join. Then we have a list that are curated by people on Hackaday. Some of them are Hackaday editors, and others are like private lists. But here is a list of staff curated list, for example. So if you're looking for Arduino projects, just click on this icon and you get everything that's tagged as an Arduino project. Then similarly, ESP or Raspberry Pi, things that fly, and so on. So it's kind of interesting, and I have to warn you, it's also something like a rabbit hole, because once you get going over here, it's not easy to extract yourself and come out of there. If you're looking for events that are happening, look on events, and that should give you stuff of what is being planned, and also all of the past events that we've had, like hack chats and stuff. If you have your own hackerspace, you can add a profile for your hackerspace over here, for example. And if you are on Tindy, and there's also a Tindy specific hack chat, so you can chat with folks over here. Jasmine Brackett is the one who keeps track of this. If there's any issues on the Tindy side, you should get in touch with us. So that's all about Hackaday.io. And then, as Anuj mentioned, there's Tindy, which is a marketplace for makers to sell their stuff. I won't add much over here, except it's pretty straightforward. There's no fees to join it. You register or you log in, and you start selling. And then if you click on learn more, it will tell you how it works in terms of what are the fees or the stuff if you sell things and so on. But it's fairly painless, fairly straightforward. A lot of people are using it, and it's kind of pretty responsive in the sense that the team keeps a lot of check on issues or problems and so on, and kind of works pretty hard to keep things moving smoothly. But there's some interesting things here. So if you have a hacker-specific project that you made and you'd like an outlet or a way to sell it, then Tindy is the way to go. And then finally, this is the overall, let's say, umbrella company that owns all of these other companies. So Supply Frame is based out of Pasadena in California, and their website is supplyframe.com, where they do a lot of professional, let's say, tools for electronic companies in terms of things like let's say locating parts and supply chain and so on and so forth. So there is a lot more that goes behind the scenes over here. It's like all the big names are kind of part of their uh, their EMS solutions and so on. But the things that might be interesting for folks like us is some access, which offers you the component library. So footprints, schematic symbols, and 3D, let's say, library. So you can see over here on the products, you have a search engine and the libraries and 3D component models. So that's kind of pretty handy and useful. There's also a handy companion website called the Component Search Engine, which well lets you look for a component and find out who's got stock of it and where you can buy it from and get a library for it or get a footprint for it and a 3D model for it and so on. There's also Find Chips, which is kind of similar. It parses all of the major component vendors and tells you who's got the part in stock, who doesn't have it in stock, and what the prices are, and so on. So again, this can be a pretty handy tool to use. That's Find Chips. Supply Face. It's called the Design Lab. It offers a lot of residencies where you can apply for. If you can pitch an idea, and if it gets selected, you become a resident, and they will walk you through the whole design iteration process from taking your idea all the way through to, let's say, finished prototype. And they have, I mean, the design lab is obviously equipped with all of the latest rapid prototyping tools that you can think of. There's all the equipment we have. We have some high-end lasers and 3D machines and all kinds of mechanical tools and so on. So a pretty comprehensive place and an amazing location. So that's the design lab, and then there's also something called Supply FX, which, well, to be frank, I don't use it a lot, although I am signed up for it. But this is something like LinkedIn or Facebook for engineers. So it kind of you can post stuff over here and you can know, get into discussions with people over stuff and so on. But to be frank, I don't use it a lot myself. It's just too many things to do in 24 hours. So yeah, that's it. I just wanted to give a quick brief overview of what the Hackaday ecosystem is all about. I will share a link to this to these slides with Anuj, who will then kind of make it public, so all of you can grab these links and make it easier for you. Anuj.
Yes, thanks, Anu. There's a bunch of stuff going on with the Hackaday and the whole umbrella of sites that it kind of manages under a supply frame. So this was a nice brief. Uh, Next, we are going to have Siddesh on here. I'm not sure. Yes, Siddesh is here. So Siddesh is going to talk to us about something that we all use directly or indirectly, and at least in my case, I'm not super familiar with it. So that's tool chains, right? Like it's like a black box that I rely on every day, directly and indirectly, but it's still a black box. So this is going to be a very nice topic, at least for me. So without further ado, Siddesh, can we start?
Yes, absolutely.
Yes. Okay.
All right. So now we begin. So what has my toolchain done for me lately? So this is essentially a, a primer on what your compiler does for you, what your runtime toolchain does for you in terms of uh, security analysis or being able to make sure that your uh, your code is as secure as it possibly could be within limits of the compiler. So who am I? I have been contributing to free software for over a decade. I'm the maintainer, I'm one of the maintainers of the GNU-C library, and I'm currently working on toolchain security. It encompasses GCC, Binitils, glibc, and some amount of LLVM as well. So this is what we're going to do over the next 30 minutes or so. I'm going to try and wrap this up in say 20 to 25 minutes so that we have some time for questions if there are any. So we're going to talk about types of security issues. It's going to be like this very high level overview of what is a security issue and what kind of issues you'd see in programs. Then I'll walk you through some interesting toolchain security features that you may or may not be using. And if you're using it, it's reassurance that you're doing the right thing. And if you're not, then hopefully this will be encouragement for you to go ahead and use these in your projects. And in the end, some good practices that I've identified over the years. Right. So jumping right in, let's look at security issues in programs. In general, security issues are essentially they're bugs, right? And they're bugs that let you do or let you make the program do something that it shouldn't do, right? And specifically, if you go into the technical aspect of it, you're looking at things like hijacking control flow, where you're exiting a loop when it shouldn't be, or you're continuing in a loop when you should have exited some time back, or you're going down the branch of condition that you weren't supposed to, right? Or you're reading memory that shouldn't have been reachable because you should have been in like a specific class, and that memory location can be accessible only in some other through some other object, or same way you're writing to it or reading from it. Then there are issues like permission barriers, right? So permission barriers are things that you would implement to make sure that you're not that there are privileged operations that you're not allowed to do, and a security flaw might allow you to do something that you usually won't be able to do, something like getting root on a system, right? That is called escalating of privileges. And then you have things like weakening randomization, where you're generating numbers that are supposed to be random, like say a one-time password, and there's a bug in your algorithm because of which your one-time passwords are suddenly predictable if you have, say, access to the last 100 OTPs. And then you have things like speculative execution, which is typically not an issue for microcontrollers, so I won't go much into it. But then essentially, it's something that CPUs do, where the final result of the computation does not get committed, but then you have side effects like cache usage, which ends up really revealing some amount of information to the malicious user. Now, again, I don't have time to look at speculative executions, but I can take questions later on if there are any specific ones. So these are just local issues, and these are not an exhaustive list. If you want a comprehensive list of weaknesses in your programs that you should look out for, MITRE has a kind of a standard list that you can refer to and educate yourself, basically. So where can toolchains help? Basically, toolchains can help everywhere. Everywhere there is a local weakness, except in cases where you have a weakness in your system setup, meaning your user access setup in your say the user setup that you have done on your box. Now your compiler won't be able to protect you against that. That is something that you have to do at an administrative level, right? Setting up policies for users and so on. So those are things that the compiler cannot do. However, within the code base, whatever you're trying to do, even things like privilege escalations and so on. The compiler has some amount of visibility into it, and it should be able to tell you what to do about it. And the runtime has a little bit more visibility because it is present as the foundation of your program, and it might be able to tell you some more about it. The toolchain can also help you protect yourself in terms of remote weaknesses, but those are fairly limited. I'll probably quickly mention that when we talk about source code fortification. So when we're looking at exploits or preventions of exploits using compilers or toolchains, we're looking at two main aspects. One is prevention, which is your compiler tells you in advance before the program is going to run what the problems or the potential problems are with your program. And the other aspect of this protection would be mitigation, where the compiler doesn't really know whether something could go wrong at runtime. So what it does is it adds some additional code so that at runtime, if you run into some exceptional condition where you're say reading or writing beyond the bounds of an array, it will immediately hit a trap and you'll abort execution, or the program aborts execution at that point. So basically what it tries to do is it tries to generate safe code. And then there's also analysis that you can do, which is static analysis, which is something that is done at compile time. And then you have dynamic analysis, which is at runtime. So now we come to the point of interest, which is embedded systems and security. And I think I've catered this more to embedded systems because I kind of reckon that that's the general crowd over here. I will talk about systems with an MMU or like larger Linux systems as well, because that kind of completes the picture. But when it comes to embedded systems, the focus is typically on hardware, and software is pretty much thrown in. And as we saw yesterday with the whole supply chain and design and all of that, there's a lot to do in hardware, and there's a tremendous cost involved in there. And a lot of times, the only place you can cut costs is in software. And unfortunately, that is where that is where bugs come in, and then you have security exploits from those bugs, right? And maintenance also for such hardware typically focuses on the hardware because conventional knowledge kind of directs that what wears out is hardware. Software never really wears out, right? So because of that, your maintenance focus is also on hardware. Software has only recently, in like the last 5 years, started getting some focus because of IoT, right? So when people joke about the fact that the S in IoT stands for security, they're actually IoT is not really to blame because IoT is really inherited that from the embedded systems, which is what it builds up on top of. And when you're looking at security issues in embedded systems, memory access bugs are probably the most common because all of the code typically runs with the same privileges, as in there's very little privilege separation, and the memory for that application is also typically mapped all together. So there's very little protection, if any, and a lot of that protection is dependent on how the program is written and whether there are any bugs in the program that allow you to read or write to arbitrary locations in memory. So because of that, the type of bugs you end up worrying about are, you can largely categorize them in two parts, although it's slightly an artificial categorization because as we see ahead, they have an intersect. One is bugs to do with stack access, stack manipulation, and the other would be general object or array manipulations outside of the stack. So let's look at stack bugs first. So primarily what you're doing with the stack pointer, or the idea of the stack in computers is fairly simple. right? There's this stack pointer register, and you're sending it all over the place, and it's literally wherever the stack pointer is pointed, that's where the stack is, right? जहाँ मैं खड़ा हूँ वहाँ से line शुरू होती है, that sort of thing. So that is very, very powerful as a concept, because of which you have this linearly growing memory location, which you can push elements into, pop elements out of, and you have this. So the whole foundation of function calls is based on that, and it's a very elegant solution, right? But what happens as a result is that with that simplicity comes a lack of check. Meaning, whenever you're allocating memory on the stack, you're never really doing any check to see where that stack pointer is landing up as a result of that allocation. And because of that, you have you could have this situation where you would go beyond what the stack is allowed to grow into, say, an adjacent memory location, which is maybe a heap or maybe some other file that is mapped in there. So that is a bug, that is a security vulnerability, right? The way that is conventionally protected is by using something called as a stack guard. Now, a stack guard is something that for the main process, the kernel sets it up. It's this one page at the bottom of the stack or the top of the stack, where the moment it hits that, you try to grow beyond it, it'll hit that guard page and it'll crash, right? So at least that's the theory behind it. And for other threads, glibc does that for the process. Now, the problem with that is that if you're incrementing your stack by a page or by less than a page, you will probably end up hitting the stack guard. But then there are ways in which you can, like using Alloca, you can jump over the stack guard into whatever is above it. And you can like, if you allocate enough space in Alloca, lo and behold, you're in the heap and you're accessing some other memory with the stack pointer, right? And that's another that's an elegant little way to bypass that stack guard protection. So the compiler has this flag called stack clash protection, which is the second option that I've listed over here, which prevents you from doing that. So what it does is that instead of incrementing, so whenever it is compiling the alloca call, so the alloca call literally just translates into a stack pointer add or subtract, right? It's a single instruction. It's very fast. So what it does is, instead of adding that value at once, like say the value is 64K or say 128K, it won't add the entire 128K at once. It will add it in less than page size. So that what happens is that whenever it hits the page at runtime, it will crash. So it will not land in the heap. So that's one very, very important protection that the compiler provides for you, right? And then there's the older option, which is stack protector. And there's this misconception that both of these are variants of the same problem, but they're very, very different problems. So stack protector, what it does is, if you have an array on the stack and you're writing to that array or to an object, let's say it's an array of size 8, right? And you've declared it right at the entry point of the function. And you start writing to it, and you write 8 bytes, and somehow you forgot to add like any check, and you wrote beyond that into adjacent memory. Now, what that adjacent memory is a stack frame information, right? The function frame information, where one of the entries in that is the return address, right? And a very common way to modify control flow is to override that return address with whatever you want. So if that buffer is user controllable, then somebody could write a special string in there, wherein the return address corresponds to like a specific point in memory, and lo and behold, you're in like a different place altogether. So this is called stack smashing, essentially, right? And the way to protect that is to use the stack protector flag, a stack protector. You can, I think there are 2 or 3 different options. There's strong and there's full as well, right? It tells you the extent, it tells the compiler the extent to which you want to protect your functions. So there, what it does is that before returning, it will check. So it has a canary word set up adjacent to the return address, and it will check if the canary word has been modified. And if it has been modified, then it will abort execution at that moment, and it will not allow the actual kind of malicious control flow to alteration to happen. So abstract protector is another very interesting flag that you should definitely look at. Then there's a relatively new concept called SafeStack, which is implemented by Clang, and it's kind of experimental, as in it's not really in wide usage outside of that ecosystem. Wherein the stack components, basically what you have on stack is local variables and your function frame information, right? So in the local variables, if you have variable length buffers, it separates those into a separate memory location. So you have essentially two stacks growing at the same time, and only the safe stuff is is stored alongside the frame information, which is the return address and so on and so forth. So that's an interesting kind of feature that Clang provides. GCC does not provide that. The other category of vulnerabilities, which is buffer overflows, right? We saw the stack buffer overflow. A generic buffer overflow would be an overflow anywhere that is not the stack, right? So you have the heap or any memory mapped file or an anonymous memory map. So if you're writing beyond bounds of objects or arrays, you might end up writing to adjacent memory locations, which if you're able to predict, you can control again the flow of execution, or you'll be able to write to data that you were not allowed to write to or read from such data, right? So there are a number of flags that the compiler provides to kind of tweak the amount of bounds checking that you want to do with your functions. So you have commonly used functions like memcopy, strcpy, strcomp, memcomp, and so on and so forth, which do a lot of this work. They kind of pick up a lot of a significant amount of that work. So these flags, essentially what they do is they make sure that all of these operations are safe. Even primitive reads, writes, it makes sure that these operations are safe. And if it finds that the operations are not safe, it will spew out a warning. Clang has similar flags as well. There is a blog post that I've linked to in the talk slides. I think Anuj has posted a link to the talk slides, which you can access later on. So that lists out all the flags, but you know what? Don't bother with the individual flags. Just use WAL. And WAL will catch pretty much everything that you would like to have caught in terms of object bounds related warnings. If you're brave enough, use WExtra, but then WExtra may result in some spurious warnings. So your mileage may vary. You try that. If it doesn't work for you, you can disable it. And if you're really, really serious about picking out your warnings and really serious about security, consider using WError, because WError will make all of your warnings into errors. So your compilation ends and you have to fix your warning. And that, for anyone who's writing any serious projects, you should really do that. Then we come to mitigation systems for mitigation feature for larger systems. Larger systems would be anything that is running Linux on it. So in this context, Raspberry Pi is a large system. And the most interesting feature over there, interesting in terms of being practical as well as fairly useful, is the Fortify source macro. You can set that macro to 1, 2, or 3. 3 will not work on GCC. 3 is Clang specific only, and it will work, I think, sometime next week when glibc 2.33 releases, because that's when it comes out. The GCC support will come out in a while, but 1 and 2 are the real interesting ones, and they've been around for a while. And what they do is, when you define those macros, the C library will replace all of your primitive function calls, like your memcopy, memcomp, strcomp, and even a lot of your network-facing functions, which is where I said some amount of remote protection, like your socket reads and writes. It will protect those with some bounds checking based on whether it is able to deduce the size of the object that is being written to. And if it finds that the read or write is exceeding those bounds, it will abort execution immediately, right? And because it depends on the bounds to be constant, so now it doesn't have to be actually constant if the compiler is able to deduce a maximum bounds because of whatever wizardry it does, that is sufficient as well. So if it finds that those bounds are being crossed, it will abort early, right? And those are constant, the bounds, because of which the runtime overhead for that is negligible. There's literally no. I would say for any out of order processor, the runtime should be zero runtime overhead, because the way the routines, in fact, the performance sensitive routines like memcopy and so on are written, it's just straight line code that goes right into the proper memcopy. It will exit only if your bounce check fails, right? So your the prefetch and the branch prediction will always go like straight through, and you will never really see any overhead in practice, right? Some of the Linux distributions are built with this, as in all of the packages in the distribution are built with this by default, right? Fedora builds this builds all of its packages with 45 source equals 2 by default. Red Hat Enterprise Linux does it as well. I think Ubuntu does it, but I'm not very sure. So this is a very, very practical protection that everyone should have. Then next come sanitizers when it comes to runtime protection. What sanitizers do is they add a significant amount of extra code. Now this is done by the compiler, not by the runtime, which does a bunch of validations. And those validations, if they fail, they can either warn or abort at runtime. And the really neat feature that I want to point out over here is a thread sanitizer, where you can also do things like detect data races. And everyone knows parallel programming is really, really, really hard, right? So any little help that you can get in identifying such things, you should grab it with both arms, right? So that's sanitizers. But then the problem with adding such overhead is that it's impractical to have in production. And in fact, that I don't know of a single production system that actually uses sanitizer in production, right? Because there's a good overhead may range from anywhere between 5 to 10%, and sometimes more. So it is a great thing to use for diagnostics or for testing, but probably not for production. The next thing is malloc checking, and this is a very versatile and very old feature that has been around in glibc, where you can set certain environment variables, they're called tunables, and with that you can get additional checking of objects that are allocated using malloc. Because now when you're using malloc, the malloc subsystem knows what the size of the object is, and it uses that to make sure that whatever reads and writes that happen in those objects, they're consistent and they don't result in any corruption. And at the same time, you have this concept of use after free, where an object is free and you end up using it afterwards. And this malloc checking will point out those issues as well. Again, it has a higher runtime overhead, and it also kind of changes the behavior of malloc, which will have like different performance characteristics. So again, this is something that is typically used only for diagnostics or debugging. But then the interesting thing is that it is debugging that you can do in production, because it is just an environment variable. So you just add that in there and run the program again, and you'll see additional diagnostics in there. So with that, we jump into some good practices that every C-based project should have, right? And the first thing is really a no-brainer. Always use WAL. If you're not doing WAL, I don't think you're very serious about your software. You should use WAL all the time, and you should take your warnings seriously. Meaning, use WAL and actually make sure that your build is clean. If you're using WAL and your build is full of warnings and you're ignoring that, again, there's no point, right? Might as well not use it. Use W extra whenever you can, but then it it can produce spurious results. So use your judgment over there. Then the second thing is probably more related to embedded systems. Typically, embedded programs are built with OS, and what happens with OS when you're optimizing for size is that a lot of the object visibility that you would have with things like unrolling or inlining and so on, they get missed out. And because of that, a lot of the diagnostics that you would have had with WAL uh, get missed out when you're building for size. So always do a test build with O2 O3 so that you give the compiler that opportunity to kind of look around once and give you those warnings. And then when you're actually building your program to deploy on your hardware, you use OS or whatever flag that suits you. Right? So this is like an important or a very useful way to make sure that your compiler kind of helps you out as much as it can. Right? Or even better, use static analyzers. The compiler static analyzers have gotten really, really good now. So the Clang static analyzer has been around for a while, and it even years ago it was producing some really useful warnings. The GCC static analyzer is fairly recent. It came out in GCC 10, and David Malcolm, who's working on the analyzer, has written a blog, I think, 2 days ago, 3 days ago, right? So he's talking about he's mentioned all of the improvements to the analyzer in GCC 11, and there's also another blog post that talks about the introduction of the static analyzer to in GCC in GCC 10. So use the static analyzer as well whenever you can. I believe it is as simple as using an fanalyze flag, and that's it. I mean, you can actually have your analysis code, as it were, in the same makefile that you have your regular builds. Then continuing with good practices, sanitizers, it's really a great idea if you can enable your sanitizers during testing, because that allows you to weed out the more obscure bugs early, and over time it kind of helps you build a sort of a software methodology, and it's something that we think very less about when we're doing embedded systems with small programs. So that's always a good thing. And use Fortify source whenever possible. If you're using GCC and glibc, there is absolutely no reason to not use it. The overhead that Fortify source 1 and 2 causes is just, I mean, it's not there. You don't really have to worry about it. Just add it and forget about it. You'll get like a significant amount of protection more than you would have otherwise without Fortify source. And the final one is slightly more contentious, which is avoid rolling your own standard library routines. It is more a personal pet peeve because I've seen people trip over themselves with this belief that they can write better routines and more optimized routines for their use case and for that hardware. And in many cases that might be true, but then it introduces a vector for new bugs. And that can often be fairly hard to find because they emulate standard libraries, and they can sometimes defeat some protection that the various compiler toolchain components provide. Custom allocators also are very tempting, rolling your own malloc or using something like JMalloc or TCmalloc. But consider tweaking the malloc tunables first. I had linked to the tunables page, manual page, a couple of slides ago. Just take a look at those. There are a lot of things that you can tweak in malloc and make it behave the way you want. And really, if none of those things work for you, then you consider using other malloc implementations or writing your own malloc implementation. And really, there are many things, and we don't have enough time to cover all of it. Things like control flow integrity, pointer integrity, and there's a lot of hardware support that is coming in as well. And typically, all of the hardware support gets implemented into your software through compilers, because it's the compiler that will actually give you all of that support transparently, so that you don't have to actually write any code yourself to take advantage of something like BTI or CET. So that is all I have. I hope I've been able to finish in time for, say, a question or two. I have not been reading comments. Maybe now it's time.
So yeah, there were a couple of questions, but your slides answered one of them, and Amit answered another. So I'll just go through the questions again.
Okay.
So the first one was by Ian, is like, how was it different from Stack Smash Protection Flag? So this was when we were talking about the stack
Right.
stuff.
Right. So the
So,
F stack protector is stack smashing protection,
right.
and
Yeah.
stack clash protection is the one that kind of protects you from jumping out of the stack into some other location.
Right. So I think your next slide explained that a little bit because Ian's next
Awesome.
message was got it. There's one other question that I had, which also was answered by Amit, but I'd like you to answer it as well. So you said my question was about how does trust zone fit into this. So I think this is about the hardware stuff that in the last
Yes.
slide.
Right. So it's not something that you would associate with like a single process. You're essentially jumping into a different context there.
Right.
Where you're so it's not something that your compiler will essentially do for you. You're depending on the hardware kind of. So you typically have this. How do I put it? So it's kind of like jumping from the CPU to GPU, I think. Although, yeah.
Right. So
If that makes sense.
everything is essentially different. Like you don't carry over any context. Is that what you mean?
Yes.
So similar to probably a coprocessor of sorts. I don't know if that's a good analogy.
So secure EL3. I don't know specifically about trust zone, and Amit probably knows better than me in that regard. But EL3 would if you want an analog, it would be something like virtualization, but an additional layer.
Right. Okay. Yeah. So
In fact,
Amit
it's called secure EL3, if I remember correctly. I want to see Amit's answer.
Yeah, I'm showing that I'm listening to his.
Yeah, so that's essentially what he's saying, which is it's additional hardware to run a different secure OS and apps, right? And then you have like an API of sorts.
Right.
Okay, so it is different hardware. Got it.
Right. But yeah, I mean, this would still be handled in the compiler of sorts, or is that just all runtime stuff?
No,
Like there
that's
would be
runtime.
no impact on the compiler, right? Like this is all
No.
what happens during runtime. Got it.
Yeah.
Okay.
So it's not even glibc. This would probably be something I think Opti or something like that, which will handle it.
Right. Okay.
I'm
Because
not
that's
sure. I
something
mean,
that
that's an area that I don't know much about.
yeah. Got it. Yeah.
That's an area
I'm just
that I don't know much about.
okay. Amit, can you hear us?
That's an area that I don't know much about.
Okay. I think he's got. Other than that, I think those are the questions. This is actually pretty interesting. What I like after seeing this stream, what I want to do is take a microcontroller and just create two tables. One, what you should be using while doing your release build, and what you should be doing while doing your production build, like the flags that you should be using, because
That's
I
a
think
good idea.
because that's how usually everyone develops, right? Like when they're
Right.
doing their development build, they have practically everything enabled, and then during the production build, they're very conscious about size and performance and everything.
Right.
So
Right.
I'm going to go through this talk and create like a table, and I'll hopefully post it soon. But unless there are any more questions, I think that's it.
All right, great. Thank you.
Thanks, Siddesh. This was pretty enlightening. I have a much clearer understanding of all the different things that the compiler does. Uh, and yeah, hope to see you around on the chat for any other questions.
Sure. Thanks.
Yes. So that was Siddesh, who was very punctual with his time. Like ended at exactly 5 o'clock. That's great precision. Next, we actually have Ayan, who's here already. Hi, Ayan.
Hi Anuj,
Can
what's
you?
up?
Yes, great. That's a very professional mic you've got, and I think the audio is already better.
Amazing.
But yeah, yes. So we have Ayan here, who's going to be talking about building FPV drones and the like what are the challenges that we as Indians face with that. It's still something that's kind of regulated a lot. I guess the regulators are still figuring out stuff. But
Yeah,
whatever
they
the case,
do.
yeah. So I'm going to let Ian take over now. And
Sure, there
yes,
we go. Hi everyone. So we'll be talking about building FPV drones and challenges in India. And trust me, there's a lot to cover. And Siddesh has already set a good benchmark of finishing in time. So fingers crossed. About me, I'm an embedded engineer from New Delhi, India. So I'm in the north part of the country, and uh, that you can see 3 layers of clothing. It's almost 16, 17 degrees here, unlike south. So yeah, most of my work is revolving around automotive, and these days I'm getting my hands dirty with automotive audio and diagnosis. So that's what I'm doing currently. Apart from that, from a hobby point of view, from things that brings joy to my life is FPV drone racing. I do freestyle piloting. I participate in FPV races around the country and outside as well. So yeah, that's one thing we're gonna be talking about. I'm a tech content creator. I write blogs. I make YouTube videos on things around that niche. So you can find me on the links on the right side. So my website is codeandsolar.com, and everywhere on the internet you can find me with the username Ayan Pahava. Apart from that, I also help organize a couple of meetup groups. So that's Hardware Hackers Club, Knife Edge RC Modeling Club, and Linux group of Delhi. So feel free to drop by and hit me up if you want to give talks there. It would be really good to have people from here to those meetup groups. Okay, so before diving into the world of FPV drones, I just want to give you a general overview of what exactly we are dealing with here. So, technical terms of calling drones are UAVs, or unmanned aerial vehicle. Scientifically, the drone is nothing but an unmanned vehicle which you can operate remotely using a RC remote, or an onboard computer, so it can fly autonomously. It can do some missions you can send it to, and yes, there are some different applications to this whole classification of this UAV, so to speak. More or less, it should take input from the ground station, and such as you can give the GPS coordinates that go to this particular latitude and longitude, drop a parachute or something, maybe for some disaster relief or things like that, or just for recreational what I do. And it should be able to send data back to the ground station, like what its current altitude and what is its GPS coordinates, which we call telemetry in technical language, and things like that. So that's about UAVs, and there are a lot and lot of different UAVs out there. So I'll just quickly show some of them. So we have three categories broadly speaking. We have a fixed wing, we have multi rotors, and we have helis. Helis, as we all know, the small helicopters. It can be fixed pitch, it can be collective pitch. I won't go into detail because that's the technical physics of how they fly. For the fixed wing, we have pusher, where you can see a military drone there, which has the propulsion system at the back pushing it forward, and then we have a puller which have a propeller in front. So that explains quite a lot. uh, the thing that excites me most are the multi rotors, which have different rotors mounted on each of the arms, which is helping it fly. And then we have a hybrid these days, which called VTOL, vertical takeoff and landing. So it is a hybrid of fixed wing and multi rotors. It can take off and land vertically, and then it can have a motion like a plane. So these are all the classifications which we have in UAVs. And today particularly we'll be talking about FPV drones. But before that, I want to quickly show you what exactly is an FPV drones and how it is different from the regular drones. So here's a video of me flying a regular drone, which you can get off the shelf from a market. So you can see you can do some pretty nascent motion. You can do pan and tilt. You can do up and down and things like that. It flies slowly. It meant for cinematic videos. So this is me flying my DJI drone at Udaipur a couple of years back. So you can see that's a normal drone, and that's what people assumes when you talk about flying drone somewhere, usually for cinematic purposes. But FPV is a whole different world, and this is me flying my FPV drones, and you can see how it's different. So that is a small video of me flying in a nearby park. A couple of years back, when there was no strict regulations, I don't fly often these days, obviously. But you can see that's a whole different world. You know, the speed, the thrill. It's like differences like flying a fighter jet versus flying a commercial airliner. So these are how I can easily put flying an FPV drone is. And coming back to my slides, so how the FPV stand for first person view, obviously. So the drone has a camera on board, which is capable of sending live video stream, and you are seeing that video stream on a monitor, and more sick on a goggles like this man is wearing here. So on this goggles, we see the live video feed from the drones, and using that video feed, we are flying the drone, we are operating it. It's just like sitting in the cockpit and doing all the maneuvers and all kind of things you can do, because you don't have to depend on your eyes, which has a very limited line of sight vision, and then you can go beyond, and you can put transmitters which are highly customizable in terms of frequency, in terms of power, and you can go to different locations and have a range in your hand. For example, you can easily do 1 or 2 kilometers on this type of setup I'm showing in the photo, and when you have the live feed on the goggles, then you can definitely operate it sitting anywhere in that range. So talking about FPV drone, what are the possibilities? So first of all, the range. We have a very limited line of sight which we can see our drone, and of course, when the drone is flying in the air, it's like a small bird. You can barely see it, especially it's if it's like a hazy day in Delhi, full of pollution. But with the FPV, you have the possibility of going beyond visual line of sight, and you can just fly your drone maneuver to a particular range, which allows by your video transmitter and camera. Recreational drone racing is one of the hottest thing coming around, and people sit in a stand. They do racing with their drones. They flew through some gates, and just tell me how difficult it used to be being let's say a Formula 1 driver. You have to have skills, you have to invest a lot of money, get training, and then the cars, and it's very easy to get into FPV drone racing, and people are putting a lot of interest in this, lot of capital in this, and this is a sport of our generation. So it's very easy for a beginner to just build a drone, keep flying, and continue practice and be a FPV drone pilot. And I just want to show you another video how FPV drone looks like. So this was again a couple of years back from IIT Delhi, one of the race I participated in. So I particularly want to show these are the kind of night drone racing where we fly the drones through the obstacles. We do the obstacle course. We two, three, four pilots, even six sometimes fly simultaneously. We do crash, but it's a lot of fun. It's a lot of adrenaline, so to speak. So that's how FPV drone racing looks like. So yes, we have some recreational part of this hobby as well. And moving ahead, what different possibilities we have in FPV drone racing is a new filmmaking style. You know, filmmaking has evolved really in a way that no one can imagine. We used to have people with the heavy cameras on the helicopter when they want to have aerial shots. That was replaced by drones, and now we can get even closer to the action thanks to the FPV drone racing. So, for example, just look at this video by one of the very good FPV drone racing pilot, Johnny FPV, and he is shooting some really high speed car drifting, and you can see how closely we are getting to the action. That was never ever possible before. So to take that kind of shot, we do have equipment, but we don't know how to do that before we have the FPV drones here. So you can just see that how close we are to the action, and that is the beauty, that is the possibility which has been open because of this new kind of hobby, so to speak. So yeah, I can see these videos all day, but coming back to the possibilities, and yes, there are much more. You can go beyond the range of visual line of sight. You can do recreational filmmaking and whatnot. So that's, sky is the limit, and maybe not. So different possibilities when we are flying an FPV drones. I just want to give a short, how the drone flies, the physics behind it, and what are the different forces acting on it, because it's really important to know what are the different factors which are involved in designing this drone and flying this drone. So this is our usual quadcopter, because it has four motors. That's why we call it quadcopter. So we need to overcome the gravity, and that is the m into g, mass into acceleration due to gravity, the weight of the drone. We need to overcome it, and we do that by producing lift, and lift is produced by this propulsion system, the motors and the propellers. But the another component which comes into the picture is the drag. That is the unwanted component. So these are all the forces acting on a body which we need to take care of when we are designing a drone, when we are writing a software for the drone, and things like that. So of course, thrust is produced by these motors, and that helps to keep this drone in air. So typically speaking, in a jet airliner, we have the lift and the drag component in this direction. The perpendicular is the lift, the parallel is the drag. Same way in case of the drone. The objective of any flying body flying in a 3D space is maximize the lift and minimize the drag. So drag is an unwanted component, but we will always have the drag. But we need to overcome it by giving it more and more lift. And the thrust is to weight ratio is greater than 1. So the body is generating thrust, the body has some weight, so the thrust is to the weight ratio should be greater than 1. That is the thing that will help to fly these bodies in air. So I told you we need to minimize the drag. So what are the things on which drag depend? What are the variables so we can play with that? So number one is the shape of the object. So that's why the planes are designed to have a aerodynamical body. We have all read in physics of class 11 the Bernoulli theorems, and body and viscosity, and spherical bodies and teardrops, all kind of things. That is where we are trying to reduce the drag by making a body aerodynamically stable, giving it more aerodynamics. We have airfoil on the plane wings for all the same reason, to reduce the drag. The other thing is drag depends on is the friction between the body and the fluid. Fluid in this case would be the air, and the body, of course, we cannot change the viscosity, right? We cannot change this viscous friction. So what we can do is we can focus on the shape of the object, and that is what we do in case of our planes. And we try to do somewhat with our drones by designing it in a way that it has less drag. But again, in drone we don't have much area to work with, so we have to do some other factors. And the second thing I want to talk about is degree of freedom. So when an object is flying in a 3D space, it has the 4 degree of freedom, so to speak. So one is, of course, that by giving the thrust, it can go up and down, of course, if you're talking about a drone. But apart from that, we have the pitch axis, that is this axis. We have the roll axis, and we have the yaw axis. So we have a 3 degree of freedom in the 3D space: the pitch, roll, and the yaw. And how the pitch, yaw, and roll is controlled when we talk about the, let's say, commercial plane, or any plane, so to speak, which is meant to carry passenger, is it has something called control surfaces. So as you can see, the elevator at the tail of the plane, it is used to control the pitch axis. The ailerons are used to control the roll axis, and the rudder is used to control the yaw axis. There are some planes that don't have rudder or that don't have aileron, and it can be mutually, it can be done without one, especially in the RC plane. But if you want to have a good control over all the 3 axes, then you need something called control surfaces. And how a control surface works is, let's say you want to give pitch up, and this is your tail. So you will tilt the tail up, the elevator up, and the air coming from this side will push the tail down, and the plane will go up. So these are the very simple, control surfaces mechanism. These are mechanically controlled in a plane. It's very different in terms of jet. Because a jet is made to be aerodynamically unstable, because if it's stable, the body will not allow it to do maneuvers which a jet supposed to do, let's say to escape a missile on its tail. So how a jet do maneuvers is, of course, it has some control surfaces, but it can also do something called thrust vectoring. So what a thrust vectoring is, you alter the position of your of the source of where the thrust is coming from the propulsion system. So this is the propulsion system of a jet, and it changes the shape, it changes the direction, and that's how it can add some more degree of freedom to what it already has. It can do some more maneuvers which a normal plane cannot do. So that's what we call thrust vectoring. And uh, we also has adopted this concept in drones, and I'll tell you how in a couple of slides. But just know that by changing the shape, by changing the direction of the propulsion system, you can achieve some more control over the degree of freedom. Okay, so talking about the drone, how a drone with no control surfaces, with no mechanical moving part, not talking about the motors, with extra mechanical moving part, how do we do a roll and the pitch and the yaw? So the answer is fairly simple. We have four different motors, out of which two is rotating in one direction and two in the opposite direction. So by changing the RPM of these motor, we can do all kind of maneuvers we want to do. For example, we want to do roll right. What we will do, we will speed up the motors on the left and we will speed down the motors on the right. What will it do? The overall thrust coming from this direction will be more than this, and our drone will take a roll right. And similarly, if we want to do pitch, we will pitch forward, then we will speed up the back motors and will speed down the front motors, and it will do a pitch forward. So that is how we obtain the degree of freedom when it comes to drone. The question is how we do it, how we know what RPM our each motor should rotate at a particular instant. And that is where the computer comes into the picture, and that is where the software, the microcontroller, the sensor comes into the picture, the control system comes into the picture. So summarizing, a drone is aerodynamically unstable. It requires a computer connected to the sensors, and it uses some mathematical algorithms to maintain the stable flight. So at any given instant, a drone will take a user input. The user input will be abstracted form of what a user wanted drone in terms of degree per second of roll, degree per second of pitch, yaw. Let's keep it generalized by saying what attitude a user wanted drone to be in air. And based on that, the sensor will judge what is my current attitude and what my user want my next attitude to be. And based on that, the software, the firmware will do some calculation, and it will speed up the motors, some motors, and speed down other motors, and it will go to that attitude. And of course, there will always be error because there are external factors. There are air, this gravity is working on the drone all the time. Maybe a high gust of wind comes from some direction which we need to counter. So to counter all these variables, we have some control systems in place. And particularly speaking, we have something called PID, or proportional integral derivative. I'm not going into the details, I'm just telling you, throwing some jargon so you can Google what that is. But that is a algorithm control system that is keeping a drone stable even when a lot of external factors are acting on it, even when there may be some fault in the motors, because you can see they are all the four same motors, but maybe while manufacturing, this motor get some additional winding, this has some friction, this has some less lubricant. So all these factors are taken into consideration when the algorithm is deciding what output to give to this motor. So that is where the software comes into the picture. And now I'm going to talk about what are the different components that you need to have in place to make a drone. So first of all, the component, we'll talk about all the component and what it needs to make them. So first of all is the frame. The frame is actually the body of the drone on which all the components are mounted. And when you are choosing a frame, you need to make sure that your frame is something that is not very heavy. It's not something that is not very fragile. Because the drones can crash. You are maybe learning. It's not an autonomous drone, and you will crash into a tree or ground or something like that. Or maybe you just reverse the direction of motor and it just flips as soon as you take off. So deciding a frame is very crucial part of building a drone. A frame can be made of carbon fiber, which is what we are using as FPV drone pilots. We have chosen CF as one of the best material because it is light. It is light, it is durable, and it also has some downside because carbon fiber is can conduct electricity, so it can give some interference to the signal of our remote as well as the camera. But the life is, I always used to say on the drone that life is full of trade-offs and you need to find the sweet spot. So a few drone pilots have found carbon fiber at the sweet spot. It's already very expensive, so if there are other options like wood, and again, finding the right wood which is not very dense, which is not very heavy, it's also very important. So and then we have plastic composite, so it's a die casted plastic material, and I'm seeing a lot of new frames are coming in this composite material. The good part, it is not conductive, so it gives you good reception all the time. And then we are seeing some combination of carbon fiber and aluminum, that's 7075 aluminum, the aero grade aluminum, and carbon fiber and composite for the parts which are very prone to damage. So all kind of things. And the manufacturing process which involves making frames is, of course, computer numerical control machines. You have laser cutters, you have water jet cutters and things like that which are making frames. The second most important component, so to speak, is of course the motor. And when we talk about drones which runs at a very high speed, we need a brushless motor. So this is a three-phase induction brushless motor, so to speak. It has an RPM per volt rating. It has some particular torque. It can take a propeller on top of it. So internally it has some windings, it has some permanent magnets, and some casing which are die casted of this metal you are seeing here, and of course a shaft. So you can see three wires. It's a three-phase motor, and because it's an induction motor, and we cannot run a drone from a power supply of 220 volts in our home, that will not give you much range. That's why we use something called electronic speed controller. So this converts the battery DC voltage into three-phase AC, which is required for running those motors. So ESC, it's known as electronic speed controller. It does two functions. First of all, it takes the battery DC input and converts it into what motor is expecting. Second thing, it also takes input from the flight controller, which I'm going to talk about in next slide, and it speeds up or speeds down the motor to a particular RPM. We also have propeller, of course. It doesn't look the super fancy component of a drone and something that can be taken off for granted, but trust me, it's the first component I would pick before designing any drone. And as Anul mentioned, I also have a course on Hackaday on building FPV drones, so there I'll talk about every component in very detail, so you can check that out. We have a power distribution board because we have four different electronic speed controller. We have four different motors, the propulsion system. That's why they are all running from the one battery. Therefore, we need some sort of power distribution board, or you can also get away with it by just soldering wires each other, but that's not very tidy, right? So we have power distribution boards to do these kinds of connection. Nowadays, PDBs are also integrated into the flight controller as well. So that's a good thing. But again, if you destroyed one, you will destroy all. That's the brain of the drone. It has some sensors. It has some CPU. Generally, nowadays, it's STM F7 CPUs because, FPV drones flying at 150 miles per hour, you need a very precise computation, very fast computation. That's why good CPUs are needed. And you can check that out. It has sensors in the form of IMUs, accelerometer, barometer, magnetometer, gyroscope. And that's, of course, the battery, the lithium ion, lithium polymer, lithium iron. That is the new generation of lithium batteries, and lithium high voltage. The cell has more voltage than the normal 4.20 volt of other families of lithium batteries. And of course, the transmitter and receiver, you can get away with by making an autonomous drones that can take the input directly from a laptop. But if you are someone like me who takes thrills of flying it yourself manually, then this is what you need. Of course, if you want to do some live transmission, then you need a camera and a video transmitter. So the photo I'm showing here is of analog generation. This is an analog camera and an analog transmitter, which works on 5.8 gigahertz. And these antennas as well. But recently, the FPV industry is moving to digital transmission, with the DJI and other companies are coming up with more and more high definition transmission, 720p. So I'm pretty sure that they're gonna soon be obsolete, because analog is a really crappy feed, and it feels like you're watching Doordarshan when you're actually flying a drone. I show you the video. That video was not from this camera. That video was from GoPro. What we see inside our goggles is actually worse than Doordarshan. So a lot of statics out there. But that's a downside of analog, and hopefully everything will be soon replaced by cheap high definition transmission. Of course, the software is very much needed, as I mentioned in the beginning of the slides. And talking about software, so you can write your own firmware. You can take some open source project like CleanFlight, Betaflight, and you can configure them as per your drone requirements. And these are really good open source projects. I particularly like Betaflight the most among them, and do contribute to that as well. But this is really a really amazing project which is developing at a very very high rapid speed to keep up with the development in the industry. And then you can have some miscellaneous. For example, this is the telemetry radio to check the drone speed, altitude. This is a GPS you can mount on the drone. This can do two different things, like it can tell where your drone is right now, and you can set a home point and trigger return to home, and that this will bring your drone back to home where you launch it off. This is a transponder. We use it for race. So this is an IR LED, and on the race first gate, it's a IR receiver, and it tells what is my lap time, which we use for FPV racing. And this is the gimbal to stabilize the video. Trust me, this is not needed nowadays because the drone are getting very very stable thanks to the software. And but again, if you want, you can use it. So drone challenges in India is definitely our civil aviation regulatory body, Director General of Civil Aviation. And trust me, I have shown you all the different components, all this here. And people think that these are the actual challenge when coming into a drone industry. And maybe we cannot make frame in India, maybe we cannot make motor in India. But trust me, I have been there since almost 6 7 years in the industry, and I have made all those things myself. I have seen other people's making it in India. There is no challenge in making this, in manufacturing this, whether you want to go for small batch, whether you want to go for uh, a mass production. There is no such challenge in manufacturing these components or these drones in India, or even to sell them. The actual challenge lies in this regulatory body. But before that, I want to tell you what are the general challenges in drones. So first of all is the capital. Yes, drone making is very very expensive, and you need to spend some bucks to make it. Is getting cheaper by the day, but it's still expensive compared to your usual other hobbies. There is a steep learning curve in this. Definitely you need to learn, and these two go hand in hand, because you invest, like, let's say 50,000 rupees, and building a drone, you get all the parts, and then you just plug in your lithium ion battery in the reverse side, and then all your ESC, your flight controller, will spark up, and they will never see another light of the day. And this do happen quite often. I remember Sahaj doing something on his live stream one day, and there was a fire all around. So yes, these things are dangerous. Speed is involved, and lithium is involved, and crashing at 150 miles per hour with a lithium battery on board, it's really really dangerous sometimes. Of course, the legal aspects, which we're going to talk about in a bit, you get outdated pretty easily because it's developing at an enormous speed. You just wake up and you just see there's a new protocol, new faster protocol of how EAC is communicating with flight controller, and you just get outdated and you just want to quickly buy another set of flight controller. And this is my favorite, video chala gaya. So it happens a lot when we flying analog, and you just want to take that shot flying 75 miles per hour on top of a beautiful lake you just saw, and then suddenly video chala gaya. Maybe for some reason, maybe that area has some interference on 2.4 gigahertz, 5.8 gigahertz, and then your drone is just gone. So these are the actual challenges of this hobby. Talking about drone challenges in India, and coming back to DGCA, Director General of Civil Aviation. So I agree with people making the law, because when you have a flying camera in air, and it can easily goes into people with wrong intention, in wrong hands. That is really a threat to people privacy, to security, and to national security, so to speak. But yes, that's always a case, and that will always be a case. But still, the rules which are being made by government bodies, regulatory bodies around the world, needs to just dial down a little. I just want to show you a few rules which DGCA, the Director General of Civil Aviation, which is the regulatory body of India, has come up with. And I just want to talk about how impractical they are for just a recreational pilot like me to fly a drone in India. So first of all, you need to register your drone. You need to give your Aadhaar card, your photo, things like that. Okay, we can do that. And then you need to do a pilot training and registration, and you need to be an 18 years old to do that. the 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 champion of international drone racing league happened in Dubai was 13 years old, and if he was an Indian, he couldn't register and fly a drone in this country, and that really sucks. So yes, another challenge, and I don't know why you need to be 18 years old or just have an engineering degree to fly the drone, because it's totally bullshit for me, and you don't need that. And NPNT is like one of the worst thing that they have come up with. It's no permission, no takeoff. So every time you fly a drone, you have to take a permission from the DGCA in their application on the website. And we all know how government website works. And I'm just waiting on a field, getting my permission before flying a drone. The sight of it makes me sick. Imports, getting my drone confiscated, my drone part confiscated, because there are no laws. And yes, that sucks as well. Range and height limit. So 15 meters is what they are allowing for a person with a drone less than 250 grams of weight to fly, which is not much in terms of me, because I can just climb a building 6 stories high, and I can just fly that, take a photo from my phone. So we just need to just dial this down, and someone needs to go there and tell them that this is not good. Beyond visual line of sight rules. So FPV is totally illegal. You cannot fly FPV. You need to have your drone always inside where you can see your drone. So that is the current rule of India. Maybe they will change, because there at this moment there is no visual beyond visual line of sight rules. So every time you fly a drone, you need to keep in your line of sight. No other rules. Spectre rules. You have to have a spectator with you to fly the drone. So basically you need another people always. So you have to be two people flying a drone, one flying a drone and one seeing it. So that's another challenge. No flying zone. So they have come up with the red area where you cannot fly the drone, and almost 75% of the country falls under that. And how good would that be? Especially comparing to country like New Zealand, which are actually promoting drone pilots and tourism people on tourism for drones to capture their beautiful country and just promote tourism from that. 75% of country in no flying zone. That doesn't make sense to me. Insurance rule. You need to have an insurance for your drone. That is kind of a bittersweet thing, because I know these drones are dangerous and it's good, but there is no insurance company in India which is selling insurance for drones as of yet. So without that, you cannot fly the drone, and there is no company for that. So another challenge in India. So on that note, that was all for my presentation today, and I hope that people who are making the rules, people in the stakeholder community, would come up with some dial down rules in future. But as of now, no flying. Thank you very much.
Thanks, and that was pretty comprehensive. I think I'm going to have to watch that on slow speed, because that was a very dense presentation. We have a couple of questions. I didn't want to bother
Sure.
you when you are talking. So the first one was from Amit. Amit's like, have you been challenged for flying drones before? Do you need to carry some kind of license with you?
Yes, so many times. So every time I try to fly drones and there is some law enforcement body around there, they do come up to me. I don't have a license because India DGCA is not giving any license as of now, but I do have my drone registration, which I carry with me, the printout of it, and I show them. How it works for me is letting them wear my FPV goggles while I fly the drone. They are quite helpful once they get to see the live video feed, and they do enjoy, and they let me hang out after that.
Nice. So the next question is from Rohit, who's another Delhiite. He's wondering. It's an open-ended question. He would like to know your take on building something like Fion 230. What's a
I have
good place
yeah.
for? Yeah, go ahead.
Yeah, definitely. I don't have any idea about this particular drone 230, Fion 230, but yes, building drone is always fun, and it teaches you a lot. It teaches you a lot, definitely, in every aspect of what I just said, physics, electronics, soldering, and things like that. And the best part is, once you crash it, because you're gonna crash it, you can repair it yourself. So DIY over buy.
Are there any good forums that you recommend for good communities where people are helpful when someone is building their own FPV?
Sure. So Beta Flight, the project which I talk about, has a very good Slack group. The Rotor Riot community, the flight test community, you can Google on YouTube, and as well as if you're into autonomous drones and drone swarms, like 100 of drones flying together doing some things, then DIY drones is a very good community. And one older drone community is Ardu Pilot, which is amazing community of people building drones uh, with the very elite flight controllers like Pixhawks and Ardu Pilot Mega.
Got it. Okay. There's another question. There's actually a couple more questions. So one is from Sitesh, where he's asking, "Is NPNT necessary for all drone sizes?"
Yeah,
Do we
that's right. That's right. So nano category, the drone which falls under nano category has to be less than 250 grams of weight, and you can only fly for 15 meters, as I spoke. And NPNT is not necessary for those kind of drone if you are flying in a green zone. So that's a really important clause there. If you are flying on a green zone, then no NPNT is necessary. But if you're flying in an orange zone, that means you need to take a permission before flying. Then you definitely need NPNT for it. And no company has implemented NPNT in their firmware as of now. So again, a gray area.
Okay. So there's a lot of regulations I see that have been implemented, but there's not a lot of on ground. What can I say?
Infrastructure.
Help for all of the on ground infrastructure
Right.
is a bit missing here.
That's right.
There's another question from Anul. So, how do the powers that be differentiated between aero modeling and drone flying?
I think I didn't get the question. How do the powers that we
Yeah.
differentiate?
So aero model. So, what's the difference between basically aero modeling and drones? Right. So, aero
Uh,
modeling is around for
okay,
a
so
while in 2000, right?
yeah, so the aero modeling community is around from like 80s or 90s, where people build airplanes from a foam board. The new drone pilot would like to call them aero modeler, but somehow that community is resistive and they don't want the drone pilots to call themselves aero modeler, because classically aero modelers are something to do with the RC planes and the helis. It's a bit clash between these two communities, but again, they are flying models, whether it's multi-rotor, whether it's fixed wing. They both are doing it for recreational. So yeah,
Yeah.
that's that.
I mean, I think there's a lot of overlap there, but there's still kind
Yeah.
of distance.
Anul said that's the only difference I can guess is the onboard camera. That's right. So the aero modelers, they like to fly the plane's line of sight, do some 3D flying, but also the aero modelers do some FPV on planes. So what they do, they build their planes in such a way that they can put a small camera in front to do the FPV as well. So that's also the aero modelers I know they are doing from a long time. So it's not new for them. Yeah, but that I don't think that's a difference between those two, because they also like to do that stuff.
Okay, great. I think this was a great session. We went a little overboard with the time, but
Yeah,
thanks,
sorry about
Ayan.
that.
Actually, this was very informative. Thanks, Ayan. Anand is here already. We are ready for the next talk. Anand, can you hear us? I think you're muted, Anand.
Yeah, I mean, I can hear you.
Yeah, great. Thanks, Anand, for that amazing talk. It was very dense, very informative, and that's something that I'm sure excites everyone when it comes to flying drones. So the next talk that we have is Joy of Programming from Anand, and Anand, I'll let you start without any further delays.
Yeah, just a moment. I'm sharing my screen. Can you see my screen?
Yeah, we can see your screen now.
Yeah, great. Thanks, Anuj. It's my pleasure to speak at the Maker conference. I'm not a hardware hacker per se. Maybe I can call myself an amateur. Let me kind of start with giving introductions, like where I come from. So I work for an organic foundation now. I've been writing programs for about 2 decades now. I've been pretty active in the open source community, and I also do trainings and train people professionally. So last few months, I've been trying with an idea of teaching programming to young children. And there are a couple of things that I've picked up while in their experiments. I would like to kind of share with you. So first, like, why did you learn programming? At least for me, it was like I learned because it was fun. There was no real other motivation. So one thing that I really like about programming is like it's a really wonderful medium where you can explore really powerful ideas. So this is a quote from Simon Propert, the creator of Logo programming language. So it's really, the question is like, what are the wonderful ideas that we want to explore using programming? Now, when I started exploring what's a good way to teach programming to young children, I realized there are two things that may actually work, and started exploring in those two directions. One is creative coding, other is hardware. So I'm going to show some of the experiments that I did, and then maybe ask for some of your inputs at the end of it. So one thing that I feel is when you want to teach programming to young children, so one thing that's important is it's not really about instant gratification. You don't want to build an application, build a mobile app or something that will give you instant gratification. You want to actually focus on the first principles so that what you will learn will be helpful for you after a decade or two, right? I mean, that's the important part. So here's what I thought. So let's say take this challenge. Given Python programming language and ability to draw a circle, what all can we do? So I'm quickly going to uh, uh, take you to an editor and actually show you what all is possible. Okay, so I'm just going to quickly walk you through what all we can do. Right, so that's a circle. So this is the ability that we have. Okay, I'm going to put a grid for a reference here. So this is the only functionality that's given to us. What all can we actually make out of this? So my idea is when you want to learn programming, it's not really about the syntax of the language or what are the wonderful libraries that you can use. It's really about how do you take simple ideas and combine them to actually make bigger and bigger ideas. So let's start with a simple circle. I want to draw one more circle. Let's say I want to put circle next to it, or well, should change the x-axis. So here what we're doing is basically circle takes the x coordinate and y coordinate and the diameter of circle. So the top left coordinate is 0, 0. So we could put two circles. Let's say what you want to put one inside of there. So I could say that's maybe it's a donut. So I can even define a function. Ability to draw a donut given x, y, and d. So what you can do is instead of hard coding these things, you can probably use relative to what value is given there. Right, this is d, and I'll probably put half of the diameter here. Now we can actually say donut 200, 300, and 100. That will give you a donut. I can probably, since I have defined that as a function now, I can put as many donuts as I want. So let's try something else. Let's say we have the small circle here, and let's say put a circle to the left and put one more circle to the right. So I'm changing x coordinate to get that, and I can do the same thing for y. Put one above and put one below. That would kind of make it complete. I can actually put one bigger circle, keeping all of them together, because this is 100, 100, 100, total becomes 300. But it'd be nice if we can actually give a name to it. I'm just going to call it ball for lack of better name. So it's going to be x, y, and it's going to be d by 3 because it was 1/3 of the circle. So I think I'll just take this one. So I'm going to reduce on the both sides. Similarly, I do for. So what we're doing is actually taking a very simple idea of drawing a circle and using it to. Oops, I think I forgot to draw the bigger circle here. That's this. Okay. Now we can take this function and draw it at, let's say, right. So what we're doing is taking this very simple idea that ability to draw a circle, and then creating higher and higher complex shapes using that. So we have a donut and a ball. Let's actually see if we can actually create a concentric circle, or I'll just say so we're going to loop to so let me kind of actually say n is 5. I want to draw concentric circles of 5 concentric circles. So I'm going over that, and I'm going to draw a circle x. So x, y, and we define x as 300, y as 300, and it's going to be I into delta, which is whatever the size that we want by n. So let's see what we get. We get concentric circles. Now what we can do is now we can actually convert this into a function. Take x, y, d, and n. And probably don't need all of them. We are getting that as inputs. So, so let's kind of see if we can use this. Oops. Yeah. 100 and 100. So that's, we draw. So what we did is started with a simple circle and then created a donut, a ball, and a concentric circles. So what all can we do? Okay, so one thing that we can possibly do here is see if we can put them in a grid. Okay, so what I can do is write a function draw grid. It takes how many draw circles in a grid. So what it does is it takes n and then puts so many circles. So all you need to do is for I in range, or let me kind of start with simple loop for I in range. Let's say n. I'll define n as let's say 5 here. So draw a circle x, y, and d. So let's say x is 100, y is 100, d is 100. So you're just going to draw one circle. But what I can do is define 100 there, or so it's a width. I'll take width by n. So x, what I can do is I can say I into d. Let's see what happens if I do that. So it's kind of drawing the circles there. So to fix it's starting from half of it, so I fix that by adding a d by 2 here. Can do the same thing by actually adding one more loop there for jn range n. So right, so that completes that. So what I can do is I can define a grid. Sorry, convert this to function. Draw grid x, y, and sorry, take just x and n. So what I can do is I can say draw grid 10. It will draw 10 circles. So right now I put show grid to kind of for reference. I'll remove that. Okay. Now the interesting thing is now could you start with just a circle and they can do so many things. Okay. Now instead of circle, what if I want to do some other shape? So what I'll do is I actually pass the shape as an argument, which is any function that can draw itself. So I want to draw 10 circles, or you can say 10 donuts, or you can say 10 concentric circles, or I can say 10 balls. Right? So what we're doing is taking a simple idea of a circle and then kind of doing using the same thing for to create more and more abstract things. So that's, I think, is one way to kind of learn programming. Start with something very simple idea and then build more and more on that. So kind of to summarize, I didn't kind of do the last part, but for the interest of time, so we started with the circle. We made a donut. We made a ball. We made concentric circles. We put that in a loop, and then we got the same thing put in a grid and donut in a grid, etc., etc. Okay, so let's now try something little more. Okay, so let's go back and actually see if you can actually add a bit of randomness to it. Okay, so what I'll do is I'll import random. So what I'll do is instead of concentric circles, I'll actually do a random concentric circles and actually see the kind of wonderful stuff we can do once we add a pinch of randomness. Okay, so what I'm doing here is 10 times I'm just going to draw a circle with so random not random gives a value from 0 to 1 randomly. I'm just going to draw a random circle. So let's see what we get if we do that. So if it's run every time, it gives a new one. Okay. Now, what wonderful thing we can do is we can actually try this put this in a grid. And that needs to say what size of the grid. So if you keep trying, it keeps giving new shape. So that's the second part. I'll not go into the third part. We can actually do even more variations on the randomness and actually make really beautiful shapes. Now, what else can we do from first principles, right? I mean, so another challenge you could take is, let's say you were given a shape of a fish, and then how can you combine to kind of make more interesting shapes? So here is something that you can do. I'm not going to go into the coding at this point for this, but you can actually take the fish, you can do a flip or do a rotate by 90 degrees or rotate by 45 degrees, or put the same image one above the other, one beside the other, or combine these two to kind of make it a 2x2 grid or a 3x3 grid. Once you have these primitive operations ready, you can actually take these things and then the one which is rotated by 45 degrees and can combine them in interesting shapes. So you can make these kind of tiles, and then you can combine the tiles to kind of make even more complicated shapes. As you can see, this is actually two of the so I call it tile 1 and tile 2. So this is basically tile 1 put twice. Here I have tile 2 in the center and then 2 tile 1s, and then I put the same thing rotated and then put it on the 4 sides. That starts making really beautiful shape. And you can go on and you can actually scale down and put it, and you can go one more level and one more level. It's really beautiful, quite a complicated shape. All we started with was a simple fish shape like this. Okay, so these are the fundamental, these are the powerful ideas in programming that you can actually try. So the inspiration for this is actually called a square limit. It's a painting by Dutch painter M.C. Escher. You can Google for this to find out. Okay. Now I thought, like, when you want to teach programming, what you should really be teaching children is actually these kind of powerful ideas, not really about how do you make an app or website or etc. These are kind of what I would call the utilitarian approach of learning something. You want to learn something because you can do something. Okay, so I think that's quite limiting. What I feel is we should learn something to actually explore more and actually figure out what all things you can do. So now I was also kind of trying to approach that similarly from the hardware, but I'm not an expert in the hardware space. So I was I did some experiments teaching interfacing with hardware, etc. with kids, but my experience is pretty limited. I'll share what I've done. Okay, so how do you start, right? I mean, you start with light and LED. Just connect a LED on a breadboard and light it. Put a switch, put a potentiometer, put an LDR. That's all you can do. Let's say you want to blink an LED. Now this becomes really complicated, right? I mean, it's so hard even to just blink an LED in hardware. Maybe like I'm an amateur and don't know much of hardware here. Well, so the only two ways that I know is you put a timer, and that's really hard to explain, like how the timer works for someone who is completely new. Or you can use a microcontroller. I've tried with BBC Microbit. It's at least not so hard to kind of explain. So playing with V's microbit, etc., was kind of not too hard. So tried with kids blinking LEDs and then making traffic lights, etc. But the different microcontrollers work differently. And once you have microcontroller, you can actually add different sensors and kind of do a lot more stuff. But what next? So I wasn't kind of, so I'm someone who want to kind of start from first principles and kind of go step by step and actually build more and more on what you already know. So I kind of stopped there. I haven't really explored further than that. I would really love to hear your inputs. So one thing that I'm quite passionate is to kind of try and see if these ideas can actually be tried at slightly larger scale. So one thing that we're doing at Force United is to see if we can actually create a learning platform where we can create courses for the community and by the community, wherein we provide kind of materials and whatever resources required to teach, and reduce the barrier to kind of teach someone, so that people in the community can actually take that and actually work in their community to kind of teach these ideas. So we're still in very early stages of what we want to do, but I would love to kind of hear your inputs on that, especially on the hardware side. And that's about it. And I want to know, like, what all other powerful ideas can we try with programming hardware? So thanks, and you can reach me at Anandology on Twitter, or you can join Force United Telegram group. I'm open for any questions.
There's a lot of appreciation about how people started their first programming, or even the circle thing that you were showing. So that reminded a couple of people about the pictorial language section in structure and interpretation of computer languages.
Yes. Yeah, in fact, that's kind of inspired from that. And the second one, I haven't showed the fish thing. Okay, so there's actually picture language in SSCP using the same kind of constructs.
Right. Yeah, but this is actually quite interesting, and I'd love to see what a hardware version of this does. Right, like because this is just first principles, and like Siddesh was mentioning, like the first principle is like without any programming involved, you need just an LED, a battery, and a switch.
Yeah, so
right?
so in fact, I was actually trying to do that, and actually I bought an 8x8 LED matrix to see if you can actually use it like a set pixel kind of thing. Then I realized it's not. I can't approach it from first principles because it has 16 pins, and the pins you need to use a board, and it uses a cycle to kind of turn on and on each one of them independently. So that's kind of quite complicated hardware, and it's too hard to kind of explain to someone who is completely new. So I felt like it's probably not a good idea to kind of try on that.
Yeah, I think there's some scope to reduce it down more. I think my first project was actually a binary clock. So so a couple of LEDs on a breadboard, and I remember I think I used an Arduino, but essentially just taking something like that which you can understand easily in programming context, and then moving that over to hardware. But yeah, I'm curious about like you said, like what kind of stuff people should start with when they're learning hardware programming from first principles.
I don't know. I mean, I don't have an answer for that. I would like to kind of engage with the maker community and then kind of see if we can come up with something really good.
Yeah, I agree. But even I'm curious. Let us know how that goes. And thanks, Anand. This was a very interesting talk, and we hope to see you in the comments and such. Right. And our next speaker is here. Amit, can you hear us?
Yes, I can. Can you hear me?
Yes, loud and clear. So this is the last talk of the 2-day conference that we've had. But this is something that I kind of asked Amit to do, because whenever I get a new laptop, one of the first things that I do is find out some blog on how to configure ACPI for good battery or good power management, and that's the only surface knowledge that I have of this whole thing. But this is something that everyone in Advantage uses, no matter what system you're on, and that's why I wanted to like, because I knew that he's experienced in that. That's why I wanted Amit to talk about power management in Linux, and here he is. Lucky for us. So Amit, if you're ready, we can start.
Yes, can you see my shared screen now?
Yes, we can.
All right. Okay, so this is going to be a whirlwind tour because I'm basically trying to, again, try to go from first principles of power management. I was told that a lot of people here are either electrical, electronics engineers, so I'm assuming certain knowledge as part of this talk. So let's see how quickly we can get through the basic stuff to get to be able to answer more questions. That's what I'm primarily interested in, if people have something. So a brief introduction about myself. So I'm a software engineer. I like dabbling in hardware. I'm currently building PCB Kingdom with Akshay Sharma. We talked about that yesterday. On the software side, I'm mostly a Linux and Zephyr RTOS developer. I've been hacking around the kernel for a while. And for people who know a little bit about power management, my Twitter handle is idle thread. Idle thread is a very important concept for power management, and especially in the CPU side. So I've worked at various companies, primarily in power management and systems software areas, so Lenaro, Canonical, Nokia. And on the hardware side, 96 boards was my attempt at trying to get a standard specification around which you could build boards, regardless of which SoC we were interested in, and a standard set of peripherals that could be brought out. For this talk, I am going to take a very, very simple SoC hardware architecture. It typically is the red box is the ARM processor. There is some buses that connect the various peripherals that you have. So you have some memory controllers. You have a peripheral bridge here. There is a system controller, which has your PWMs, your watchdogs, other things. Various devices and buses, so CAN bus, USB, etc., etc. Your memory controller obviously is connected to your flash, SRAM, and then everything has some interface either to user space or other pieces of hardware. This is a very, very simplified version of what modern SoCs look like, but I think this is good enough for the purposes of this discussion. So, roughly speaking, power is directly proportional to the performance. So, the higher your performance in terms of the gigahertz or whatever else you want to call it, the more power you typically consume. This has especially been true in the Intel world as they've cranked up the gigahertz. And some introduction to mathematics at this point. So your power consumed by your CPU is essentially dynamic power. It's the short circuit power and the leakage power, all of it combined together. So at this point, for this talk, we're mostly focusing on the dynamic and the leakage power. The dynamic power is probably the biggest component of your CPU power that you are trying to minimize. But also with modern manufacturing techniques, so when you hear about nanometers, whether it's a 5 nanometer process or people are going for the 3 nanometer and trying to get that working soon, there is a lot of leakage involved there. And so that component of this equation has been going up constantly for the last 10 to 15 years. So that's no longer something that can be ignored. So coming back to this, so yeah, when your capacitors in your circuits, basically the logic gates that are constantly toggling on and off, that's your dynamic power consumption. And the property of the transistor, so the sizes of your transistor is where your leakage power comes from. And the short circuit is when the state changes happen simultaneously, which causes short circuits in the circuit itself. But yeah, as I said, we'll focus on the dynamic and the leakage for most part. So continuing forward, so we know that power is roughly proportional to V square F. What that means is that it is square of the voltage and directly proportional to the frequency, and the constant is C. So if you reduce frequency of your processor, you will linearly reduce power. But if you reduce the voltage at which your processor is running, you will actually have a much larger effect because of the V square effect. So I hope people remember this part of physics, math, electrical engineering from their school days. If you look at a typical mobile use case, these are typically your power guzzlers. So let's say you're talking about, when I say internet phone, I'm basically talking about a video call. So you have your display and your Wi-Fi obviously are consuming a lot of power. Wi-Fi is constantly sending data back and forth. Displays showing that video in high resolution. Your CPU isn't as big power draw because a lot of the video information is being directly offloaded to the GPU and the display controller. So it's not, CPU isn't involved in that path as much. And then there's the audio chip for the sound to be playing and whatnot. Something a little different is the GPS navigation at the end, where your GPS unit is actually a big consumer of the power. And you have a display because you might have a maps application that's constantly on trying to show you where to go to. And CPU is involved because it could be because the GPS data is the application that's processing the NMEA data from GPS could be running on your CPU. So this is roughly what the use case looks like. Now, going back to the good old days of hardware. So this is like 15-year-old hardware. Linux, it was a much simpler world. I mean, you had a clock framework in the Linux kernel, which essentially you would basically toggle the clocks on and off. So it is also, in hardware terms, it's also called as clock gating. So you would toggle the clocks, and you could reach so-called power saving states, but there wasn't really a lot going on. In a lot of cases, the CPU was just busy looping. That's it. It was just busy looping, and they didn't really care about power as much. On the ARM side, they actually did care about it a little bit, and there was an instruction called WFI, wait for interrupt, that the CPU could execute, and it would just wait there until it was woken up again. It was saving some power, but not a whole lot, because you still couldn't turn off your regulators that were powering the CPU, other stuff. And there was no concept of saving state and whatnot. So this is a very simple model in the Linux kernel of how power management was being modeled. So you had LDM, which was the Linux driver model, the device drivers. There were some suspend resume hooks in power management, and your SRAM idle, so you could put your memory to idle, and then WFI, which is the special instruction to put the CPU into sort of a power saving state. Now, what happened is that as voltages kept going, as frequencies kept going up, voltages kept going up. So to run faster, you also had to ramp up your frequencies to the CPU. And as a result, the V square component of your power started becoming very important. And so that's when the CPU FREC subsystem was introduced in Linux, which would allow you to target specific operating points. So they were called operating points because you could say that I want to run at 500 megahertz or 750 megahertz or 1 gigahertz. And that frequency had a corresponding voltage associated in an operating point table for most CPUs. Mostly because that was when how the characterization of the silicon was done. So when a TI or Freescale or Qualcomm produced a chip, they characterized it at different operating points, and they would tell you. So I used to work at Nokia then, and they would TI was our silicon supplier, and they would tell us that we have characterized that the silicon will be stable at these operating points. So this frequency paired with this voltage. Anything outside that is not characterized, which means we cannot guarantee you that it will continue to work properly. So that's why CPU FREC and operating points were introduced to the kernel. The next step was idling and regulators. So what happened was that there was an obvious observation that we had all these regulators that were powering different parts of the SoC that were turned on all the time. And so a regulator framework was essentially created to manage these regulators. It wasn't just about turning them on and off, it was also about sharing regulators, because a single regulator could supply voltage to not just a CPU, but different peripherals as well. And so you could make requests to the regulator framework to say that I want this regulator to supply 3.3 volts, etc., etc. And that's what the regulator framework handled. And once everybody said that I no longer want that regulator, you could actually turn off the regulator, which actually saved a lot of power. Similar thing around CPU idle. Now, with CPU FREC is useful when the CPU is constantly running things, right? You are constantly running things, but let's say I'm just reading an article on my display, and I'm not really doing much on the CPU. So at that point, you are able to reduce your CPU frequency while still keeping it active, because I don't need that processing power, because I'm not compiling a kernel in the background or anything. I just need it enough to do all the display refresh task and the background task if necessary, like fetching email or something. So that's the active use case. That's what CPU FREC is used for. The idle use case is when my CPU is not being used for anything at all. And and this is happening at the millisecond scale or even less, microsecond scale. So at that point, you are basically saying that I could actually turn off my CPU for those time durations when I know there is nothing required. And again, part of that is the wake. There's wake up timers that actually wake up your CPU every time there is something to be run on the CPU. So based on looking at the timer queue, you could basically say that I have nothing to do for the next 100 milliseconds. Let's just idle the CPU. That's where the CPU idle subsystem came from. And PM quality of service, PMQoS, that box that you see, is a way for device drivers to say that I'm not going to do anything for a long time now, or that I need the CPU to be on because I'm going to be starting some DMA transactions, or I'm going to be doing something very soon. So basically keep the CPU from going idle. It was a constraint system to allow device drivers to express a constraint saying, don't go to idle. Going forward, we started having SMP systems. And as soon as we started having SMP systems, there was obviously more complexity, because if one CPU was off, the other might not be off. And if they are being powered by the same regulator, what that means is that you cannot turn off the regulator until both those CPUs have been turned off. So again, regulators that could previously be turned off as soon as the CPU had nothing to do, no longer could be turned off that easily. Obviously, the nice solution would have been that every CPU have its own regulator and whatnot, but that increases hardware costs, it increases complexity, other things. And so you didn't want to do that in all cases. So CPU hot plug was a subsystem that wasn't actually created for this use case, but it was actually misused to deal with a lot of this type of thing, where you could force the CPU offline by basically hot plugging it out of the system. So Linux basically, all the data structures related to that CPU were destroyed, and Linux, as per Linux, that CPU no longer existed in the system. So that was CPU hot plug. And after that, more complexity, you had clock and power domains abstraction for peripherals. So far, we only had clock and power abstractions for the CPU itself. But now we are starting to look at peripherals, because the peripherals were actually taking up a lot of power, essentially. Just keeping them on because of the buses. They would keep some buses on, and they themselves were big consumers. And so runtime PM was created to actually manage these peripherals. This allowed for very, very fine-grained access to the clocks and regulators feeding each of the individual peripherals, not just the CPUs anymore. All right. At some point, people were like, okay, these peripherals we are able to turn them on and off, but there are also different performance states for peripherals. So an example is MMC. So MMC, as per the spec, can run at different frequencies. So you can, depending on which voltage has been supplied to the MMC controller, 1.8 volts, 3.3 volts, your MMC card could be written to at different frequencies. And it's really up to you for your use case to select how I want to drive that peripheral. So if I run it at 1.8 volts, it means that my writes to the MMC card will be slower, but it also means that I might potentially save some power. Not always, but I might save some power. So performance points for peripherals allowed us to basically control that aspect. So the OPP framework the OPP framework and the runtime PM, basically together they allowed us to have that control over the performance of peripherals. And then finally, there is the thermal. So thermal, as far as I see things, thermal is like a big hammer. It's like it's kind of the veto power of power management. So what I mean by that is that nothing if there is a thermal alert, your system is in trouble, and there is no way you can work around that without actually satisfying your thermal alert, right? So if a system has been characterized to run at 4 gigahertz with 8 CPUs active, it doesn't mean much on if you are thermally throttled at, say, 80 degrees Celsius. Okay, so all those specs don't mean a lot. What really means is how long can you sustain yourself at, let's say, whatever that number is. It could be 80 degrees, it could be 90 degrees, depending on what kind of cooling solutions you have in place in your system. So thermal is that veto power. It's that big hammer. Nothing, you cannot exceed that. So if it's 80 degrees, you have to basically manage your power envelope within that thermal envelope. If you don't, things are just going to get bad. The silicon is not going to be able to sustain that performance, and it'll start misbehaving, which could lead to crashes and random errors that you don't want to. So thermal framework is also part of power management if you look at it from that angle. So thermal framework has some vendor policies and a thermal manager which sort of corrals all of these together. Okay, so that was a very, very brief introduction to the power frameworks. But are we there yet? I mean, is this a done problem? And so what I'm going to talk now is something that's happened roughly over the last 7 to 8 years, maybe 9 years. ARM introduced a new type of SoC architecture called as Big Little. Essentially, what that meant is you could have two different types of CPUs, okay, with two different microarchitectures on the same block. And what that meant is that you would have an extremely fast but power-hungry CPU and a not so fast but very power-efficient CPU running together in a single die. And as you can imagine, what happened as a result of that is that suddenly your power budget depended on where your application ended up being scheduled. So if your task or whatever your application was, if it actually ended up running on the big CPU, it was going to guzzle a lot more power. It was going to and it was going to finish faster. But if you didn't need to run that fast, or if you didn't want it to guzzle so much power, it would make sense for you to actually have it scheduled on the little processor, which was a lot more power efficient. But how do you do that? Because so far, I mean, until 7, 8, 9 years ago, Linux had no concept of asymmetric CPUs. According to Linux, as per all the data structures inside Linux, as per everything that was part of Linux core kernel, the assumption was that all CPUs are equal. So if you boot a system with 8 CPUs, all of the 8 are expected to be equal. Big Little broke that assumption in a very huge way. And it wasn't just about Big Little. I mean, we were coming to the point where even on Intel architecture with the symmetric CPUs, it was actually mattering because because you have multiple clusters, multiple islands of CPUs, and if you could schedule intelligently, you could actually turn off one of the clusters completely and save a lot of power. You didn't want both your clusters to be on at the same time. If you could pack those tasks onto one cluster and turn off the other cluster. So that's where we started the work around integrating scheduling decisions into power management. So what was happening as a historical lesson is that the CPU FEC and CPU idle subsystem weren't actually cooperating a lot. So they both took decisions independent of each other, and they were both catching up on each other's decisions. And the scheduler was not involved in the decision-making function. So essentially, all of these three components, the scheduler, the CPU FEC, and CPU idle, were essentially taking independent decisions which were actually going against each other's decisions. There was no coordination. And this is what that looks like in picture. So you have the scheduler on the top, you have CPU idle to your left and CPU FEC to your right. They have their own governors, which are essentially heuristics. These heuristics basically allow them to pick the next state for CPU idling and pick the next state for CPU FEC. So what is the next frequency I want my CPU to run at? What is the next idle state I want my CPU to run at, and that sort of thing. And so they were all working independently of each other. And now think about this. Now, if I'm the scheduler and I'm moving a task from CPU 0 to CPU 4, okay, I know that the load on CPU 4 is going to increase and the load on CPU 0 is going to decrease, right? But the scheduler wasn't telling anybody about this. It was just doing this. It was just moving that task along. What could have been done a lot more intelligently was that it could have sent a notification to CPU FEC system and said that your load is going to decrease in a few hundred microseconds because I'm doing this task migration. And so it could have taken a proactive decision and said, I would kick off a CPU frequency transition and reduce the frequency on CPU 0 and increase the one on CPU 4. So this is what we started working on. So basically there would be a common scheduler task placement. There would be some heuristics, common heuristics in the scheduler. And then the decision of which is the next state to pick would be actually made from the scheduler. So this is something we started working on. It took a while to wrap our heads around the problem because scheduler is a very complex piece of code, and we were struggling with knowledge of the scheduler. We understood the power management features very well. We understood the power management frameworks very well, but we couldn't. We were still learning about the scheduler. So that it was like a 2-year process while we were learning about this stuff. Before we could even talk the same language with the scheduler maintainers in Linux. And so we tried a bunch of different approaches. All of them were essentially knacked by the upstream maintainers. So Ingo Molnar, who's one of the key scheduler maintainers upstream, he's also Linus's, I would consider him to be one of the key lieutenants of Linux, of Linus Torvalds. He basically said that the entire landscape, power saving landscape, is fragmented. I mean, the policy decisions are taken everywhere and there's no centralized location. And essentially he said that all that policy has to move to the scheduler. So he's going to knack anything that takes incomplete approaches. So we had been taking, admittedly, we had been taking incomplete approaches for like 2 to 3 years because that was where our expertise lie. And he was now saying, no, it's no longer acceptable. We need to bring all this information and all these things into the scheduler. And so that's how that went. So along the way, we did solve the problem. It's still being solved. I mean, there's still a lot of work going on there. But along the way, we actually ended up solving a lot of problems. I mean, the power topology of the SoC. So I talked about clusters. So power topologies of SoCs, essentially, if you have on the die, if you have, let's say, 2 CPU clusters with 4 cores each of them being driven by a regulator. So it's essentially one regulator, one cluster, then another regulator, another cluster. And then there could be your caches, your per CPU L0, L1 cache, a shared cache for that cluster. Let's say that's an L2 cache. And then across the clusters, so the cluster 1 and cluster 2, you could have another shared cache like L3. And so that was your power topology of your entire CPU cluster. So there was no such concept in the scheduler. We introduced that. We assumed all cores were equal. So Linux assumed all cores were equal, and we fixed that. So now you could boot a system which had different capacities. So capacity in Linux terms is essentially a normalized number from 0 to 1024. So you could basically say that my CPUs 0 to 3 have capacity 1024, which is the maximum capacity, and my CPUs 4 through 7 have capacity 512, which is half of these. So you could essentially say that these 4 CPUs have half the capacity, which means they have half the processing power of these first 4 CPUs. So we introduced that concept. There was the integration of the idle task into the scheduler, so that the scheduler was the one which was picking when a CPU should idle based on intelligent scheduling. There was something called scale invariance, which I will come to in a minute. But essentially, it means that before scale invariance, the load metrics. So when you see top and you see those 3 load metrics, right? Your instantaneous load, your 5-minute load, and this thing, they were essentially wrong under CPU FREC. So if I'm running a load at 500 megahertz, and let's say it says it's 20% of the load, that load becomes 10% at 1 gigahertz. But that's not correct. I mean, it's the same load, it's the same workload on the CPU. Just because I'm running it at a different frequency, it doesn't mean that the load changed. But that's how we were doing the math around it. And so we had to introduce a correction factor called scale invariance to fix that. And then there was now a new governor called schedutil, which would allow all this policy decision that Ingo talked about from the scheduler. So this very quickly defines what the scale invariance utilization is essentially. So without the invariance, if you were running at so you've got to look at this top and bottom first row, so no, with no invariance. So the first column here where it says, okay, it's running at 1 gig.
I think there's been an issue with Amit's stream. Let me try and fix that. You know what would be really funny if Amit lost power in a power management talk. I think that would be very poetic. But let's just wait for a second. In the meanwhile, if anyone has questions, please feel free to ask them in the comments. Are you dropped from the call 30 seconds ago? Yeah. Yeah. Okay, I just spoke with him on the phone. He should be back in a minute. Sorry for the technical issues, guys. Hi, Amit.
All right, sorry, I didn't notice that. So where did you last?
A minute ago.
So I'm
we
almost
finished the
scale invariance. Okay.
After that.
Okay, I will start there again. So let me share my screen again.
Yeah, I was just saying, if you had a power issue in a power management talk, that would be very poetic.
Yes.
Okay, I'm going to drop. You can...
Is this good now?
Yeah, this is good. This is good.
Okay. Yeah, so let me rewind one slide really quick. So yeah, this was the scale invariance. So without scale invariance, the load will show up as double or a half depending on how you looked at it. And with scale invariance, the load will end up being the same in your load calculations, even at different frequencies. And so we solved other problems regarding workload automation. We created a lot of tools to help simulate these workloads, show to the maintainers, show to the community how the issues we were seeing around scheduling, around power, and whatnot. So yeah, so I mean, problems. Now thermal management is also becoming part of this entire framework. And this is what the Linux stack looks like right now with respect to power management. So I don't expect you to read all this and every bit of there, but it's just to show that it's fairly complex. We jokingly say that we've created ourselves jobs for life with this complexity, but in essence, it's just the sheer hardware complexity to manage all of this. That's gotten us to this place. Here is a summary of the various types of power management frameworks and what they are called in the Linux kernel. So clock trees are managed by the clock framework, power supplies are managed by the regulator framework, so on and so forth. So I've already shared my slides. If you want to go back and have a quick look at that code, here is in general where I would want to go dig into if I wanted to look at power management code in the Linux kernel, latest ongoings and EAS. So there's some links there. There are some references to energy aware scheduling. There's energy models that are currently used. Essentially, energy model is a table which says, okay, this is the cost of running a task on a certain type of CPU. And so now that information is available to the scheduler, it knows where it should schedule a task depending on users' policies, whether I want to optimize for power or performance. And I believe I'm done. Sorry, I mean, this was quite quick, but there was a lot of material to cover.
So I have a couple of questions. I've already asked them in the comments here. So one was, so thanks for explaining the heterogeneous computing thing, right? Because I see that that's like having heterogeneous co-processors is becoming more and more common. I mean, even if you look at Apple, they have like 4 or 5 different types now, and I think that's bound to catch up more and more, right? What I had was this is this recent trend. I saw at least 2 chips. One is STM and one is Renaissance, who are also including Cortex M, which is like a whole different ball game, right?
Yeah.
Into this. My question was: is the kernel management, is the power management and the scheduling stuff taking that into account yet, or that's like completely independent? Because it's the same people who are working on. Yeah, go ahead.
So STM, let's take that as an example. So STM has the MP1 chip, right? And the
Correct.
MP1 chip is I think what you were referring to, where they have
Yeah.
a dual Cortex A7, I believe, and
Yeah.
a single Cortex Cortex M on the same chip. But you have to remember that they're running different OSs. So
Yeah,
typically,
so that's what I was coming to. Given that Linux Foundation is now guiding the kernel, the Zephyr project.
sorry.
Does that the Linux Foundation is now guiding the Zephyr project, right?
Exactly.
Which is so.
Yeah.
Does that influence anything?
So coming back to the STM, so the Cortex A would be running Linux in this point, right?
Correct.
And the Cortex M would be running something like Zephyr or another RTOS, free RTOS or anything else, right? Now, we aren't actually doing anything to coordinate between the different OSs in terms of power management. So if that is the question, no, we aren't doing anything. But you have to remember the reason these chips have been created. So the idea here is that the Cortex M running Zephyr, FreeRTOS, whatever, any RTOS, would be the one that is constantly alive, pinging the sensors, gathering data, and then passing it on to the Cortex A7 for the processing, because they are the faster CPUs, or they can do a lot more processing. And so most of the time, the use cases being envisioned are that the Cortex A7s would be asleep most of the time. So the Linux side will be sleeping most of the time.
Right.
The Cortex M would be gathering sensor data and then waking up the Cortex A's periodically with an interrupt. Right. And that's the only time they would be running, do some processing, and then go back to sleep. So there's no cross OS PM happening here.
Right. Do you see something like that? Yeah, I mean, with this architecture that you mentioned, that doesn't really make sense for the kernel, because it's anyways asleep, to manage anything on that other than probably firmware.
No, it's literally on a wake up and sleep method. So
yeah, got it.
The Linux literally goes to sleep on the Cortex A's, and they get woken up every time the Cortex M has some new data for them.
Right.
So you manage it at that level. Whether you could do this more intelligently through hardware, I'm sure you can, but I don't think anybody's doing that yet.
Right, but I'm guessing this is going to be an increasing trend. We're probably going to see more of this, I guess, at some point. Yeah. I had another question. Actually, I have one or two more questions. when you were talking about thermal stuff, right?
Mhm.
I was wondering upon what kind of damage does overclocking or other things have like cause? Like, does the kernel is the kernel aware that something like that has happened, and does it change its behavior after that, or it's all hardware at that point? Like, if there is
Uh,
permanent,
the answer is that the kernel can do only so much.
right?
Eventually, it is up to the hardware to handle this. So most Intel silicon, I know for sure, handles this, and a lot of the high-end codecs. So ARM silicon also handles this, where they have this thing in hardware which says that if my silicon temperature goes above 100 degrees, 120 degrees, whatever they have set it to, they just shut down to prevent damage to silicon. Otherwise, yes, there is a serious risk of damaging the silicon.
Right.
If you have sustained temperatures above that magic number, whatever that number is, 100, 120 degrees, if you
Right.
sustain the temperature, there is a chance that you will damage the silicon. Now, what the thermal framework in Linux allows you to do is it allows you to set trip points. So you can set up trip points at 60 degrees, 80 degrees, 100 degrees. So way before you actually get to that temperature, and you can set up policies saying that, okay, if I'm at 60, just send a warning. At 80, start throttling some things, and maybe turning down your frequency. At
Right.
100 degrees, be more aggressive, that sort of thing. So you can do that as part of thermal framework. But eventually, you have something called as a runaway processes. So a runaway processes might make it almost impossible to control your temperatures, and it could be a factor of your environment. So if I'm outside, let's say in 40 degrees weather,
Right.
and let's say I'm a phone that's kept on your glove compartment inside a locked car with all your windows rolled up, okay,
Right.
the temperature very quickly goes up above 100, 105 degrees very easily.
Yeah.
So in those kind of ambient temperatures, there's not a lot that the software can do, and it's the hardware that has to step in and literally shut down everything.
Right. So this hardware, like this, doesn't really talk to the kernel, right? This
No,
is
at that point, if it has gone to that point, the hardware won't care. It's like, I have to save myself. I'm just going to shut down everything.
got it. Got it. Okay, this is interesting. And yeah, I mean, what kind of stuff do you think is happening more, like, because growing popularity of ARM, there's a lot more very different use cases that are coming. Like, for example, I'm sure when phones started becoming popular, we weren't very worried about super high temperatures.
Mhm.
But now with edge IoT or whatever you want to call it, chips that are being designed to be used as CCTV cameras or whatever, are there more aggressive profiles that are coming up? So you mentioned something about each thing has a profile basically now, energy profile, right? Each chip
Mhm.
seems
Energy
to
model.
energy model, sorry, not profile.
Yeah.
So does that incorporate like very aggressive stuff? I'm
Um,
talking about
so I'm not
one.
I'm not sure I understand the question. Aggressive in terms of what?
So, for example, I'll name names. Raspberry Pi starts throttling at 80 degrees Celsius. So
Yeah.
what's the most kind of the highest that something goes in that situation? Like, what's is
So
there some,
you have to remember that the actual temperatures don't directly correlate to. I mean, just because something throttles earlier or later is not directly an important thing to keep in mind. So, for example, Qualcomm hardware that I've worked on,
right?
they can work just fine at even at up to 105 degrees. So you can keep sustaining that. And the shutdown is like emergency shutdown is at 120 degrees. Okay. Now, this
Right.
is a factor of the manufacturing process as well. So it's not just a factor of
Got it.
absolute temperature. It's how
Right.
it's the characterization that has been done to get your basically your circuits have to be stable at a certain temperature, and that is definitely there's physics involved there. And if your manufacturing process can take care of that and dissipate the heat as quickly as possible, then you can keep going at a higher temperature longer.
So the only point that Linux actually cares is the trigger points. They might shift a little, but that's the only thing that the kernel cares.
Exactly. So if you look at the device trees, there are device trees for all these boards like Raspberry Pi and Qualcomm boards and whatnot. You will see there's a thermal section, and they will have trip points defined, and the trip points will differ from platform to platform. They can even differ from device to device. So the same chip, let's say I use a Qualcomm 845 processor, right? The Snapdragon 845. Now, if I were to use that in a phone versus if I would use that in making like a laptop type of form factor, okay, they have completely different thermal profiles, because a phone is a smaller device, which means it has a less amount of area to dissipate the same amount of heat. Whereas a Chromebook is a bigger chassis. It has more area to dissipate all that heat. And so you will be able to keep it running at, let's say, 100 degrees for much longer.
Right. So, and I think this is going to be a lot more common because, for example, the M1 chip from Apple comes in a bunch of different form factors. The Pine guys are using the same chip across multiple devices like the phone, the tab, the laptop.
Yes. So that is where you would have different thermal profiles for the same chip in different form factors.
Right. Okay. So yeah, that makes sense to then put that in the device tree, because then that's where all the platform stuff is going to go anyways.
And eventually, if you say that, oh, I want water cooling for my laptop for whatever reason, I mean, that's fine. That means that you could go and change your device tree and say that, oh, I don't care about 100. I can maybe pump up to 110 because I have external cooling, or because I'm running this in a environment. Let's say I'm in a room which always runs at 5 degrees Celsius. It's a data center somewhere. It runs at 5 degrees Celsius. So you can go even more, go at higher temperatures, because you know that you have the capacity to dissipate all that heat.
Right. You bring up an interesting point about the data center. So the data centers is there's a lot of ARM CPU racks that are coming up, right? Like, because we could have realized that its price to performance is better and the performance is almost there yet. That's similar to what these thermal profiles we mentioned, right? There's no other difference, or do we have different kinds of server chips, and does that mean there's different kind of power management that's going on?
So there are server chips. I mean, technically, their ARM architecture, they have similar constructs, but they're obviously designed for enterprise workloads. So everything from the bus widths and everything is optimized for that effectively.
Right. So it's a different ball game, kind of.
Yeah, exactly. But sorry, I mean, somebody is really trying to. Yeah, so effectively, so enterprise chips are. The other thing about enterprise chips is that they also tend to use ACPI for their firmware to handle a lot of these complexities. So things like regulator clocks and other things, they handle that, all those dependencies and those transitions and everything in firmware on a different microcontroller. So that microcontroller, embedded microcontroller, is where all the firmware transition is handling, and it's not being handled in Linux. Linux only says I want to go to this state, and that's automatically handled by the microcontroller.
So that's the PMIC that we commonly hear.
It's no. This is something other than the PMIC. It's another microcontroller.
Okay. Right. I see. The
They're using
PMIC is
the embedded controller, I think.
okay. 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 Correct. Uh, I think that's about it when it comes to questions. This was pretty informative. I think I love the part where you talked about we how we started with like symmetric processors and then we had to adopt, and that was like probably a longish process to kind of make that work. But I think that's going to play an important role even going forward. Uh,
Yeah.
Thanks
And, and,
for
and I think even Zephyr, for example, is taking the same approach. I mean, Cortex M, it
right,
started very simple. I mean, you could
right.
do very simple things with for power management, but now I think very increasingly, Zephyr is starting to add more sophisticated power management features because
I mean, I'm starting to see dual cortex processors, dual cortex
exactly,
yeah. I mean, yeah, I mean, even there's like heterogeneous asymmetric processors on microcontrollers, which is
exactly.
insane. But we are here. So yeah, I mean, that's the other thing that I was actually wondering about. This is not directly related to Linux, but like the stuff that's happening in Zephyr, right? Because those guys are heavily influenced from the kernel guys, and most of them are like you, who've coming from a kernel background, right?
Yes.
So I'm guessing that, and that's not necessarily true about most of the other RTOSes. So I'm very curious about how Zephyr is going to tackle these problems going forward, because there's definitely a lot more complexity being added, like every
So,
new chip.
so I think there's a lot of sharing of ideas that I think
Device based,
Zephyr is borrowing a lot of ideas from the Linux kernel because,
right,
as you said, a lot of the maintainers at Zephyr are actually ex Linux kernel developers.
right,
So there's a lot of back and forth of those ideas. As and when the microcontrollers start getting more complex, we'll start seeing a lot of these frameworks. So they already have device tree. They're starting to have more sophisticated power management.
right.
We're starting to have more sophisticated scheduling now. So I think this complexity will increase over time.
Yeah,
It's inevitable.
I mean, like you start with a mini Linux in Zephyr, and then you graduate to Linux kernel development in a few years.
I hope not, because Linux does not scale down to those sizes. So I mean,
Yeah,
I
of
can run
course.
Zephyr on a microcontroller that has 64K of flash and memory.
Right.
There's no way I can do that with Linux anytime now. I mean,
Yeah.
I think last we tried. I think even fitting it into like I think 4 megabytes. Some people have done it, but it's very hard to go below 8. Anyways, I mean you have to hard code things out and remove them physically. It's even just saying all no config in def config in kernel config in Linux. It still
Right.
creates a kernel that's huge
Yeah.
by Zephyr standards. So I don't think we will get to that point, and I think Zephyr is very mindful of that fact that it still needs to run on tiny microcontrollers as well.
Makes sense. But yeah, in general very fascinated by how Zephyr is tackling this, because there's a lot of experience that they're carrying forward
Hmm.
from the Linux part of their source, or
So
out of their
yeah,
stack.
modularity is the key here. So you have to make every subsystem modular so that I only compile it in if I need it, and that's the only
Yeah,
way I can keep the size down and the memory usage footprint all of it under control. So I think that
yeah.
they're being very strict about that in the Zephyr community.
I think some of the other approaches that other artists have taken, for example, free artists, is that they just don't care about things like power management, for example, right? Like they are just focused on the core things that an artist should do,
Yeah,
and that's what they stick to. So, like seeing power management stuff being tackled by Zephyr folks is going to be pretty interesting.
yeah.
Uh, I think that's it. I think we were very yeah, the like similar to Ion's presentation from earlier, there was a lot of information packed into this. So I'm definitely going to watch this again because this is all very interesting, and yeah, there's I knew it was complicated and complex, and there were a lot of parts in it. But this probably makes it a. I mean, I'm more overwhelmed, honestly, about this now than ever before. But
Yeah, I mean, it is. It can be a little overwhelming to start with, but yeah, I
yeah,
think you can actually find your way around once you know where to look and just focus on small areas of. You don't need to know everything on day one, I guess.
yeah, definitely. But yeah, I mean, it's interesting because it goes like this power management stuff goes from right from, like you said, scheduling all the way to the kind of case that you have, for example, right? Like you said, you can tweak stuff for a water cooled case or something. So there's like this whole like it touches everything, like right from the chip level to the kernel to what kind of a case or cooling that you are including. It's insane.
Yeah, it's power management is always you go horizontally and vertically across the system. So
Yeah,
we had a joke at Nokia where all these device driver developers. So so there were people who were developing drivers for like the serial buses, I2C, Spy, blah blah blah, and there were
right,
people who were doing audio device drivers and video device drivers, blah blah blah, and then they would get everything working. Would get everything working nicely, and then the power management people would come in. That is us, and we would turn on power management features by putting our patches in, and everything would go to hell. I mean, everything would just stop working because most of this stuff had been designed without power management in mind,
right,
and without things like clock gating and things going to idle and being woken up by interrupts and resuming processing from there and then on. So basically saving state and restoring state and then continuing processing, that sort of thing. None of that had been taken into account when they were developing the device driver. And then as soon as
right.
power management was turned on, all this would break all the drivers, and then you would spend the next 2 months fixing up your drivers to work with power management.
Yeah. We have a late question in here. It is not directly related to what we've been talking about,
Okay.
but the question is any interesting things Zephyr has done for debuggability on microcontrollers?
Um, debuggability on MCUs. So, I mean, other than providing all the tools that are already available, I mean,
Right.
all the JTAG stuff and
SWD, I guess that it supports that.
all that is already integrated into Zephyr. So,
Yeah.
ST-Link or what is the
Black Magic?
yeah, I mean Black Magic, but I'm talking about the what does Nordic use?
Sagar. J-Link.
Sagar,
Sagar J-Link.
J-Link,
Yeah, yeah,
J-Link,
yeah.
Sagar or J-Link. So I mean, all of those tools will work out of the box with
Yeah.
Zephyr because they have
Yeah,
done all wrapping of the tools with the binary. So if you have all those tools installed on your system, you'll find
yeah.
it and be able to run it.
Yeah, that's one thing that I've noticed. Like across all RTOS, is the debugging story is more or less the same because those tools are by themselves. It doesn't care if you're doing bare metal or you're doing an RTOS or whatever. It just works.
Yeah, I mean you can do it. So the nice thing I like about small devices is you can do things like I can quickly quickly add a line to my SPI driver on my I2C driver or GPIO driver to blink an LED whenever it hits some state it shouldn't. So I
Right,
kind of know that I'm hitting a state that I shouldn't, and I can go and debug that. So
right,
instead of depending on print case, because print case sometimes change your timing constraints, and so if it's a timing related issue, then
right,
it's really hard to trigger that as soon as I add a print
right.
statement in there.
Yeah, I mean,
So
in microcontrollers, that's pretty straightforward. Yeah,
yeah, so I mean those things are very easy to do here.
yeah, yeah. That's why I'm starting to get into kernel development, but I'm a little apprehensive of that because I'm used to adding just print statements and serial logs whenever needed. But yeah, yeah, yeah. There's some other comment about Twilio and Memfault doing some good stuff. that stuff. But yeah, Memfort is one of those good companies in the microcontroller world who are doing some interesting stuff. I think those are it about the questions. Thanks, Amit. This was very informative, and there's a lot to think about and a lot to read about here. But this was very interesting because, like you said, this is something that touches everything,
Yeah.
like it or not, right? And it's pretty. I guess it's important to have like a little bit of understanding, even if you don't directly work on it, to know about this because yeah, this is going to impact you a lot.
Yes. Thank you very much for allowing me this opportunity, and thanks for
Yes,
organizing this. I had a lot of fun.
yes. Yeah, this is yeah. I mean, yours is the last talk, so after this, we're basically done. So yeah, I'd like to thank everyone who came and spoke. Thanks to someone like who you and Anul who spoke twice. And yeah, I mean, this has been great. We covered a wide variety of topics. Like we went from like compilers and power management, 3D printing and flying drones to good programming stuff like the one that Anand talked about. There's a lot that we covered, and this has been great 2 days that I have been able to enjoy. Uh, and yeah, we'll all anyways be in touch on the Telegram group, guys. If you're not on the Telegram group, it's Makerville. You can just search it on Telegram. I should be able to join it. And there's of course Makerville.io, which is the forum where we discuss long form posts or questions or other things. Thanks to all the speakers. Thanks to all the folks in the comments who are talking about the things that they appreciate and questions and everything. And hope to see you around.